Hello, good morning, good afternoon, good evening, and welcome to the Randomness Summit, a virtual conference about the state of the art in randomness beacon research and deployment. My name is Karola Kirsanow, and I'll be your MC for today's event. I'll be introducing speakers, taking questions, and occasionally making lame jokes. I'm a research program manager at Protocol Labs, and we're an open source R&D lab building the next generation of the internet. And the next generation of the internet is going to be built on randomness. We're super excited to present a fantastic lineup of speakers on a wide variety of topics surrounding randomness beacon technology. I can see we have an amazing crowd with us today. Over 500 people will be attending the summit from over 50 countries. From Argentina to Vietnam, we have attendees spanning 6 continents. Just got a hello from Mexico. We have an incredible mix of hackers, researchers, engineers, founders, makers, builders, and just curious folks from all walks of life. I'm really glad you could join us. I'm going to start today's event off by talking a little bit about why we're hosting this summit. Then I'll give a brief overview of the structure and schedule of the event, what you'll be hearing, and from whom, and how you can participate by asking questions. And then I'll end with a bit more about the history of randomness research and a description of the League of Entropy's new Drand beacon, so that we're all ready to hear from the first speaker. Let's jump right into it. First, why this summit? Well, randomness plays a vital role in nearly every aspect of our daily lives. Voting systems, traffic management, and financial services all depend on randomness in some way. But randomness plays an especially critical role in internet security. Most of the crucial protocols we rely on in our daily work, for secure transactions, for encrypted communications, for lotteries, are built on a layer of randomness. And keeping the steady stream of random numbers flowing has not been easy. This problem has occupied hackers, researchers, and engineers for decades. Our focus on randomness today is the culmination of a multi-decade-long challenge of assuring consistency in distributed systems. So we decided to create this event for us all to learn together about the randomness that lies at the core of the internet services we rely on every day. To learn about Drand and its largest deployment, the League of Entropy. And to become part of where this industry is headed by exploring the future of randomness generation. We have an amazing day planned for you, and this is how we'll be structuring the rest of the event. The summit will be divided in 3 blocks. In block 1, the first segment of the conference, we'll be updated on the current state of the art in randomness research and deployment, and learn how secure distributed randomness beacons are constructed. We'll discuss the importance of randomness to critical distributed system projects like Ethereum and Filecoin. In block 2, we'll do a deep dive into Drand, our new secure distributed randomness beacon, and the League of Entropy, the first production Drand network. We'll hear about current and future use cases for Drand and how the network will be secured from attack. In block 3, we will look to the future of randomness with an exploration of verifiable delay functions, functions that take a set time to compute, but whose output can be quickly verified by anyone. We'll learn about the hardware constraints affecting VDF computation and how the Ethereum randomness beacon plans to leverage VDFs to provide unbiasable randomness. Now let's talk some quick logistics. First, let's synchronize. This conference runs on UTC, or Coordinated Universal Time, and if I make a reference to clock time, it will be in the UTC time zone. After the first intro talk, each following talk is slated for 20 minutes. At the end of each block of talks, we'll hold a joint Q&A session with all of the speakers from the block. Now let's quickly talk about how the Q&A sessions are going to work. You can ask a question by typing it in the Zoom chat or posting a message in the Telegram group anytime during the event. We have a panel of moderators who will be monitoring the chat for questions, and passing them on to me to ask to our speakers. Although this is being live streamed on YouTube, we will only be monitoring this Zoom chat and the Telegram group for questions and comments. If you aren't in the Telegram attendee chat, you can simply head over to randomness2020.com/telegram to join the group. In some cases, depending on your availability, you might be given the opportunity to ask your question directly on camera. Please make sure your questions are simple and concise, as there won't be any opportunities to ask follow-on questions or chase tangents. ETH Global and Protocol Labs are committed to making sure that everyone can participate in our shared future. To that end, we will be following the code of conduct posted on the conference website. Please take a moment to familiarize yourself with the code of conduct and keep it in mind when interacting with other conference participants, speakers, or organizers. Now I'd like to speak a little bit about the history of randomness. From early system synchronization methods like the network time protocol, now one of the oldest internet protocols in current use, to Lampert clocks, the first implementation of a logical clock algorithm, to modern solutions like Google's TrueTime API, which uses atomic clocks to synchronize faraway databases, consistency through synchrony has powered the growth of large and complex global networks. In a truly distributed web, we can't give an atomic clock to every machine in our network, or assure that every atomic clock keeper is honest. So we've had to adopt an even more radical strategy to achieve consensus across the many and diverse nodes in our network, using randomness as a pathway to consistency. In our quest for strong randomness, we're building on a robust body of prior art in the field of randomness engineering, with some extraordinarily creative solutions. For example, the United States' National Institute of Standards and Technology, NIST, has a project that aims to produce randomness using quantum entanglement, otherwise known as spooky action at a distance. Bitcoin can produce random numbers by broadcasting random values every time new blocks are mined. And the RandHound project has created a robust and scalable random number generator. The distributed systems of Web 3.0 require a source of randomness that is unbiased by any party to operate optimally. And today, we'll hear from speakers deeply involved in creating the tools to make our random web work. Now let's talk about good randomness. The Randomness Summit is part of a celebration of the launch of Drand version 1.0, the internet's first production-grade, publicly verifiable randomness beacon by the League of Entropy. Drand was developed as a response to the question, can we make fetching randomness as simple as fetching time from NTP servers? Drand is decentralized. Its output is produced by a diverse and active network of independent parties, the League of Entropy, who are committed to publicly generating good randomness. Good randomness is extremely important to the protocols binding our information networks together, and we will hear more about why that's true in today's meeting. But what is good randomness? Well, we can start by describing its opposite. There have been cases where attackers have rigged lotteries and elections by influencing the randomness of a system. Insecure, exploitable randomness is bad randomness. Randomness researchers have defined 5 characteristics that a random number generator should have to mitigate these types of exploits. It should be unpredictable, which means that you can't reliably guess the next number to come out of the generator. It should be publicly verifiable, which means that anyone can check that a random number is a legitimately random number. It should be bias resistant, meaning that you can't lead the generator one way or another. It should be decentralized, so there's a set of independent parties that produce the random numbers. And it should always be available. You must always be able to reach the system to get a random number. Drand is a distributed, bias-resistant, unpredictable, always-on, and publicly verifiable source of randomness. Today, we'll hear why randomness beacons like Drand are integral to the future of the distributed web. Okay, I think we're ready to move out of the in-game tutorial and into the heart of the game. But before I hand the mic to our first speaker, I'd like to thank ETH Global for helping us to assemble a great conference on very short notice. We at the League of Entropy essentially launched our first production-grade randomness beacon and network, and then decided to put together a conference with our remaining momentum. ETH Global helped us to assemble our event in less than a week, after doing a similarly excellent job with HackFS last month. We think you'll enjoy what they've put together. So now, let's roll. Welcome to the first slate of talks about the current state of the art and ecosystem in randomness research. Our first speaker, Bryan, leads the Decentralized Distributed Systems Lab at the EPFL in Switzerland, where Drand was born. He is an expert in building secure, decentralized systems, including privacy and anonymous communication, system security, and blockchain technology. Bryan will be guiding us through an exploration of why randomness matters, including an explanation of what randomness beacons are and their applications for distributed systems like blockchains. Now let's all please welcome Bryan to the stage.
Thank you, Carla. It's great to be here and a great privilege to be able to start this session off and thank you for putting together such an important and wonderful event. I will go ahead and share my screen for my slides. Okay, so this will be necessarily somewhat of an academic talk. So I apologize in advance for the many of you who probably are not academics. I hope it will not be too dry. It's an academic talk because I am an academic, and specifically the leader of the Decentralized and Distributed Lab at EPFL. This talk will focus on the fundamentals of distributed randomness from the research perspective. Where did these protocols come from? What's the state of the art from the research side that led to the DRAND protocol? And I'm very glad that since our lab has been involved in this area, working on these kind of protocols for a while, I'm extremely glad that distributed randomness has finally reached deployment, full usable deployment as an internet utility. And so I hope to in this talk give a little bit more in-depth detail, both historical and technical, about where DRAND came from and what principles it's based on and what led to it. So first, before I get more into that, I want to introduce my lab, the DDIS lab, just briefly. And the main, what the DDIS lab is all about is, what motivates us is what we call the weakest link security problem. The problem that practically all of today's information systems use what we call weakest link security, where you only need to break one weak link, compromise one server or entity to bring the whole thing crashing down in terms of both integrity, privacy, confidentiality, and other properties. And as our whole computing ecosystem gets bigger and more complex, we get more data, more interconnected systems, as it should be already clear to everyone for years now that the more complexity makes this weakest link security much worse. And that's just because the more weak links they are, the longer the chains we have, the more weak links there are, and the higher probability that any one of them is going to break. Now, for decades, we've known about technologies, approaches, at least in the research world, that can in principle, turn this around to turn weakest link security into strongest link security. Where an attacker would have to break multiple systems or compromise multiple people or credentials or companies in a federation in order to compromise security. And in principle, we even know that this strongest link security, decentralized security, can even scale to not just 2 or 3 or 4 nodes, but hundreds or thousands of nodes. And it can, when it's done right, we can make security scale the right way, so that our systems get stronger as they become larger rather than weaker, right? So that's why the DDIS lab exists, to try to figure out how to build protocols that do this and make them practical. Here's a brief introduction to some of the team members that have made this happen. These are only the current team members. There's, of course, some past DDIS team members, including Nicolas Gailly, who is now at Protocol Labs and is a very central part of the DRAND project. So that's a quick introduction to DDIS. Let's move on to distributed randomness. First of all, what is public randomness? Why do we need it? Carla already mentioned a few scenarios in which it's extremely important. Lotteries, obviously, but lotteries are not used just for financial rewards. They're used for many other societal purposes. They have been used. They're used for selecting juries from an eligible population. They've been used in war drafts. And that's a particularly interesting example, because it's also an example in which the randomness has been known to go wrong. They discovered long after the Vietnam War that the randomness that was used to choose soldiers to go to their deaths in Vietnam was biased. So some birthdays were better to have than others in terms of getting drafted or in terms of not getting drafted. Much more recently, there's been lots of other situations where randomness, either electronically or in the classic physical world, has been hacked or compromised in different ways. So randomness is, it is both extremely important and also not trivial to do securely. Let's look at a few of the uses of electronic randomness specifically in distributed protocols. So obviously, lotteries and similar things exist in the electronic world, in the decentralized blockchain world, just as much as in the historically in the physical world. But beyond that, randomness is used for sampling, for picking representative groups. For example, picking a representative set of ballots to audit an election. It's used for picking representative quorums for a large pool. This is used in leader election systems like Protocol Labs is using, which they'll talk about later. It's used in large-scale sharding protocols such as OmniLedger, which I'll mention in a minute. And in general, it's often used as a very fundamental scalability tool. It's also used in proof-of-stake blockchains and for other purposes. I won't focus on these, talking about these applications very much, since a number of other talks you'll hear later will talk much more about applications. I will just mention one of the particular applications that came out of our lab, OmniLedger, which was one of the first secure horizontally scalable blockchain systems using sharding. And basically, what OmniLedger does is to divide the state of a blockchain into any number of shards, by dividing the total population of validators or miners into smaller but randomly chosen subgroups. And it's extremely critical from a security perspective that these subgroups be unbiasedly random to ensure that no attacker can compromise a majority or get too many members of any single shard, which would defeat the security. right? And so again, I won't get into the details here, but we showed as a research project that this is one of the approaches that can make blockchains extremely scalable and get essentially as much bandwidth as transaction processing bandwidth as you need. This research project is now a couple years old, and quite a number of actual blockchains in deployment are starting to use these and similar sharding approaches. And so I'm very happy to see that development. But again, this is just one of many applications of public randomness. Now let's look a little bit more closely at what can go wrong when the randomness is not as random or not as unbiased as we really need. So, of course, many things can go wrong with randomness. Now, there's unfortunately a very basic confusion that is very common is to mix up public randomness with private randomness. How many of you have probably heard of people and companies accidentally posting private keys, private encryption keys, or private signing keys on the internet, or embedding a private key in a GitHub repository that goes public. Now, that's an example of private randomness that should be private, that's intended to be private, getting leaked to the public to cause a disastrous security failure. On the other hand, public randomness, of course, is randomness that's supposed to be public. Everybody is supposed to know the outcome of a lottery or many of the other applications I've been talking about. But you just want to know that the randomness is trustworthy. And it's important to understand that you can't just use private randomness and reveal it, because then you will have to completely trust the one party that or the one device that generated that randomness. And a vast amount of experience has shown that just trusting one device or one party to generate public randomness is a terrible idea, and will go wrong in one way or another sooner or later. Now, another important aspect of randomness that is the mathematical quality or entropy of the randomness. How unpredictable is it from a statistical or mathematical perspective? And a lot of this is where hardware random number generators, especially systems that are designed to use quantum effects or other very sophisticated hardware to generate randomness. These are usually the purpose of these is generally to ensure the high quality and high entropy of the randomness. Now, this is a very important thing too, but it's different. It's a different problem from the trustworthiness. So you might claim to have the best randomness, the best high entropy randomness in the world, but can everybody trust you to, who can trust you with that claim? Do they need to just trust you on that, or can they verify? And so that's, the quality of the purported randomness versus the trustworthiness of the public randomness are two very different things, both important. But of course, in this talk, we will be concerned more with the trustworthiness aspect. Now, finally, we have to understand that even if the randomness is truly trustworthy and truly random, truly unpredictable, nevertheless, there's still a question: is it truly unbiased? Is it uniform? Or is it coming out of a random source in a way that's non-uniform in some way that someone might know? And this can also, even if it has quite a bit of good randomness, but it's biased, it's again untrustworthy, and even a tiny bit of bias can compromise many security critical applications of public randomness. So you have to understand that even even when it seems like randomness sounds good, it sounds like it's mostly not unbiased, but that's just a little bias is for many applications not good enough. And we'll see later a little bit about why. Now let's take a brief look at the academic background. Now there's a lot of different approaches known to create public randomness in the research literature and in the practice. This talk is talking about focusing on distributed randomness protocols. And there's a lot of precedent in this case. For example, I recommend as one of the much earlier papers about 20 years ago, Christian Cachan's paper called Random Oracles in Constantinople. In which was one of the first papers that used distributed randomness of a kind similar to what we're talking about here in a distributed consensus protocol. So it's very relevant background reading for blockchain and researchers and practitioners interested in these kinds of applications. Of course, there's many other ways to generate random numbers, such as slow hashes or verifiable delay functions, which will be another topic later in this event. You can also take an existing blockchain and watch it and get arguably good, arguably somewhat bias-resistant randomness. The problem is always that when you use, for example, an existing proof of work blockchain, there's always at least a little, there's always some opportunity for someone to bias the randomness, namely the miners, for example, by throwing away blocks, by mining blocks, but then deciding not to reveal them. And so, anytime there's a miner has a choice to reveal or not, that is a, potentially expensive way to opportunity to bias randomness, right? Now, it might be expensive enough that you don't care, that you say, well, that's good enough, that's unbiasable enough. And there are very good ways, for example, Joe Bonneau, who is going to speak later, and his colleagues have done some very nice analysis of how expensive it needs to be to bias the randomness that you can derive from a blockchain or from a proof of work blockchain. And so this and other known methods of generating randomness are some of the many approaches. Now, what Drand does, and what I'm going to focus on in the rest of this talk is working in what we call the threshold model, the T of N threshold model, where you assume that somehow you have some number of nodes, N nodes, maintained by separate parties, and you make a security assumption that that fewer than T of them, fewer than the threshold T of them, will be colluding to bias the randomness. Now, as long as the actual system meets this threshold, and fewer than T of them are corrupt and colluding together, the system will be secure. If T nodes do collude, unfortunately, security can immediately fall apart, and that colluding majority can defeat the security, right? So. So this is one of many possible threat models. It's a very practical one. It's in general, it's hard to avoid threshold assumptions. Other blockchain systems that often claim not to use threshold assumptions often do actually have a threshold assumption built in if you pull it apart a little bit more carefully. So this is a very basic and practical model, but of course it does have its limitations that we need to acknowledge. So with that, let's talk about ways we might, how might we choose random numbers? And to start with, let's think of a very naive protocol that you'll probably immediately see does not work, right? Let's just say we want a distributed randomness protocol that collect, in which there are n nodes, and each of them, we want each of the nodes to contribute some to the randomness. And we're going to combine, have all of them broadcast, pick a value that they think is random, and they're going to broadcast that value to all of the other nodes. And then they're all going to combine each other, collect each other's values and combine them using some mathematical function to decide the final output. Let's say we just use a simple addition function. And in this case, if all of the nodes are trustworthy, this actually produces perfectly good randomness, even if only one of the nodes actually has a good high quality source of random numbers, and all if only one node actually is producing good random numbers, and all the others actually have broken but innocently broken, not maliciously broken random number generators, like all the others are just outputting a constant all the time, then this will provide good randomness, right? On the other hand, unfortunately, this is completely insecure as soon as any one node, let's call it J, is actually malicious in a dynamic sense, in a distributed system sense. And this is because in distributed systems in general are actually asynchronous. Somebody who's malicious generally has the choice to just, for example, wait a little longer than all the other nodes. Wait to see the output of the other honest nodes before J decides on its own output, right? And so if J just waits to collect all the values of the other nodes that other than J, then J can just decide what it wants the output to be. It's going to decide on an output V, and then subtract from that the outputs of all the other nodes, and then set the result to its VJ, right? So J can just kind of reverse engineer from what it knows exactly what it needs its output to be in order to completely rig the final output that anybody provides, right? So this is pretty terrible as a randomness protocol, as should be obvious, right? Now, the first thing we might think of doing to this is, well, use a smarter combination function. Who would use addition? Why not a cryptographic hash, for example? Well, unfortunately, that only helps a little bit. So it will ensure that the output is not completely determinable by the dishonest node J, but on the other hand, hashes are still pretty quick and easy to compute, and so once J has all the contributions of all the other nodes, it can basically act like a Bitcoin miner. It can launch a whole bunch of hash operations in parallel with different possible different possibilities for its own value, and basically mine through millions or billions or more, just depending on its hardware available and resources. Just mine for the choice it likes best, and this can very easily create a huge bias risk so if you consider a lottery among the actual millions of people playing a lottery, a 1 in millions or billions of bias risk is will completely compromise the lottery. You can just win the lottery if you can mine for a 1 in a million or 1 in a billion, the best of 1 in a million or billion choice, right? So using cryptographic hashes or any simple function here does not solve this problem. So let's make this protocol better, at least less naive. So this brings us to what I call straw man 1. And this is actually used, unfortunately, it's used surprisingly often in the actual world uh, by people and groups who I think are not sufficiently aware of the bias problem, right? So strawman one is less obviously broken, and that is and here we have a two-stage protocol where first every node has to pick a random secret, keep it secret for now, don't broadcast it yet, but instead just broadcast a commit to that secret. Any cryptographic commit will work, such as a hash of the secret. That's the easy, obvious way. And so everybody first waits to collect everybody else's commits. And then as a second stage, everyone then broadcasts their secrets, right? Now everyone, and then everybody collects those secrets, checks that they match the actual commits that were sent earlier, and assuming everything went correctly, all the secrets actually do match the hashes that were sent earlier. Everyone can say, okay, looks good. We're going to use addition or another hash or anything function you want to combine the secrets into a final output, right? Now, so let's first talk about when this protocol will work. So this protocol will work if all of the nodes show up, right? So if all of the nodes, if none of the nodes become unavailable or disappear during this process, then this protocol actually will work and generate good randomness, right? Because no node will know the final output before the second stage. And as long as one of the at least one of the nodes is honest and is not revealing its secret to the other nodes to the adversary before the second stage, then that honest node will ensure that that the output is unpredictable and unbiased, right? Assuming nobody abdicates and drops off between the first and second stage. But that's the big issue, right? So what if somebody doesn't show up in the second stage and reveal the secret that corresponded to the commit they broadcast in the first stage, right? So now, well, what can we do? Well, one thing we can do is just call that a unsuccessful run of the protocol. Well, the protocol fails to run. We go back and try again. Well, we could do that. The problem is that's both a denial of service attack and a major bias attack, right? Any member who doesn't like the output that they see, right? You can still have an adversary that a malicious node J that just waits for all the good nodes to reveal their secrets in the second stage, and then the adversary gets to compute what the output will be, since only J knows what its contribution will be, right? And J decides, well, do I like it or not? Do I like the outcome? Is it good for me or is it less good for me? And if he doesn't like it, he's just going to drop off and force everybody else to restart from scratch, right? Now, it of course gets worse if an adversary controls some number of colluding nodes, because the adversary can then just pick any one of those nodes to drop off, force all of the others to restart the protocol, and then next time around, if the next round, if the adversary still doesn't like the result, he can sacrifice another node, have another node drop off to make the protocol fail and have to start over again, right? And so in this way, a colluding adversary can keep the protocol offline for quite a few rounds. The number of rounds that the adversary has colluding nodes at the very least. So it's a major denial of service attack, and it's a significant bias opportunity. Now, of course, the other thing we could do in such a protocol is just to say, well, we're going to go ahead. If somebody drops off in phase 2, we're going to go ahead anyway. and we're going to compute something just based on the outputs that did the outputs of the nodes that did reveal their secrets, right? The problem with that is, since you don't have the outputs of the nodes that didn't reveal their secrets, you have to change the set of secrets that gets combined based on that set of nodes that, the particular set of nodes that did or didn't reveal their secrets. Now, if you think about it, if there's an adversary that has some number of colluding nodes that wants to bias the outcome, say F, maliciously failing nodes, those F nodes can wait until all the honest nodes reveal their secrets. The colluding nodes can now compute, using the honest secret values and all of the secret values that they committed to, which they know because they're colluding. And they can again do basically a mining attack. They can compute in advance the 2 to the F, the exponential number of possible outcomes they would get for any particular combination of decisions of each of those F nodes, staying in the protocol, carrying it through, and revealing their secret or not, or dropping out, right? So this creates, again, an exponential bias opportunity. 2 to the F, the attacker gets to choose the best of 2 to the F possible outcomes. And if F is a significant number, if this is a fairly large federation, for example, then the attack opportunity, the bias opportunity gets exponentially worse as the system grows. And this is precisely the kind of weakest link security that we're trying to avoid in good secure decentralization protocols. Okay, so how do we actually solve this? To understand how what the real solution to this kind of protocol is, we have to understand a basic cryptographic technique called Shamir secret sharing. And I'm not going to talk about it in detail, but just give a very high-level overview of the basic idea for those who might not have encountered it before. Now, Shamir secret sharing is a foundation for a lot of threshold cryptography, threshold encryption, threshold signing, multi-party computation of all kinds. And it's a very old, well understood concept. It's a little bit more less mature and less well known in the blockchain world, but it's getting much more of a toehold gradually. So, and the basic idea of Shamir sharing is let's assume somebody, let's call him a dealer, wants to deal a secret, wants to create a secret, but then share it among, with a threshold of T among N parties, right? T is less than or equal to N. So that any threshold T of the parties can cooperate to recover or use it in some way, but any less than T parties can't do anything with it and get no information about it other than by correctly following the cooperative protocol they're supposed to, right? Now let's see how this can actually work in a super simple scenario. And I like to illustrate this, I like to use a pirate analogy. Suppose you're a pirate and you have a pirate captain, and you have found and buried some treasure on a desert island, and you want to go back and get it later, right? But you're a lazy pirate, and so you don't want to have to go back yourself to get it. Instead, you want to send some of your henchmen. Now, you don't trust, you have 3 henchmen, and you don't trust any one of them completely. So you don't want just one of them to be able to go back and steal it from you. On the other hand, you know that one of the henchmen might disappear, might die, might get killed in a bar fight or whatever, right? So you don't want to require all 3 henchmen to go back for it either. Otherwise, you might lose it entirely. You'd lose availability of your treasure, right? So to balance that, you want a protocol that ensures that any 2 of your henchmen will be able to go back and get it for you, but one henchman will not be able to find it, Okay, so how do we do this? So take your map, take your treasure map, find some landmarks on it, and you draw a line between those landmarks that goes right through where the treasure is right on that line. Okay, so it can be pretty much any line. But then now you're going to find some more landmarks that allow you to draw 3 roughly parallel lines somewhere else on the map. Now you're going to draw yet another line that intersects all of the lines you drew so far and your secret. Now now at the points where this new line intersects the 3 additional lines that you drew, you're going to mark points and call these the secret shares. Those 3 new positions are going to be the secret shares. Now you're going to draw a map for each of your 3 henchmen that gives each of them a way to find only one of those specific points, right? So each of your henchmen is going to be able to find one of these 3 secret share points perfectly based on the landmarks you provide on their respective maps. But they won't know any of the other points or your secret initially. On the other hand, now this protocol gives us exactly the properties you need, because first of all, consider if any one henchman tries to go back and get your secret. This is what they're going to see. They're going to have one of the points, their point, but they're not going to have any others. And so they can draw any number of, an infinite number of lines through the point they have, and they provably get no information at all as to where your secret is. On the other hand, any 2 henchmen that go back together, regardless of which 2, it doesn't matter, just any 2 can just draw a line through, cooperate to draw a line through their respective points and triangulate exactly where the secret is, right? Now, so this, and this is essentially, essentially exactly what Shamir secret sharing is doing. Of course, in, there's a lot of details that matter in actual implementations, but we don't need to get into those details now. Now, an obvious question is, well, does this work with thresholds higher than 2? And the answer is yes. So it just takes higher degree polynomials. So if you, instead of just lines. So if you want a threshold of 3, you want 3 out of 4 or 3 out of 5 henchmen to be able to reconstruct the secret, then you just need a quadratic polynomial. And you get exactly the same properties. And so for any given threshold you might want, there's a polynomial that will let you do that. Now, so let's go back to our strawman distributed randomness protocols and see how this affects the situation. So we already discussed strawman 1 and why it kind of works, but creates this major either denial of service or bias opportunity. Right, and the reason it fails is because any single node who might drop out can force everybody either to restart the protocol or to change the set of commits of secrets that you go into the final output. Now, Shamir secret sharing provides a solution to this. Basically, I'm going to leave out a lot more details here. But in this case, each of the n nodes acts as a dealer and deals their own secrets. So we don't want to just rely on one dealer. Instead, everybody's going to be a dealer. But then we have ways to combine these secrets homomorphically. And by doing that, we get what we call a joint polynomial, and this gives us in principle exactly the properties we want. Now, the good news is this works, and it's secure when it's done right, when it's implemented correctly, and there's various ways to implement it. It ensures that no subthreshold number of nodes who might drop off can stop the protocol from working. And regardless of which subthreshold number of nodes might drop off, they can't change the outcome. The outcome is fixed based on the commits, regardless of which threshold of nodes actually cooperates, stays on and cooperates to reveal the secret. Now, so that's the basic the basic concept that you need to understand the way secure distributed randomness protocols work. Now, I'm just going to briefly cover a couple of the more recent randomness protocols in this space that the DDIS lab built. Now, and our research focused especially on scalability. Because this protocol that I just mentioned, the basic protocol works fine, but it doesn't scale to large numbers of nodes. And we wanted to make sure that you could really scale randomness protocols to large numbers of nodes. And this led to the research we published a few years ago called Scalable Bias Resistant Randomness, where we showed a couple protocols, RandHound and RandHerd, that achieve that can scale this to large numbers of nodes, thousands of nodes. Now, to do this, what we had to do is we had to solve basically a chicken and egg problem. We knew that we could scale this protocol if we could run Shamir secret sharing among smaller groups of nodes. If we could take the big group of participants and divide them into a number of smaller groups and run Shamir secret sharing among those smaller groups. The problem is the way to do that securely needs those groups to be chosen randomly, but we didn't have randomness, public randomness to choose those groups securely, because that's what we're trying to create, right? So RandHound and RandHerd are basically trying to solve this chicken and egg security scaling problem, right? And I won't get into the details, but the key, just to give you a quick notion of the key intuition, RandHound is basically a bootstrap protocol that says, okay, we're going to assume that somebody would like to initiate a protocol to generate randomness. And that we're going to assume that party really wants to finish the protocol. And if they don't actually finish the protocol, then, well, that's their problem. And they're only going to get one chance to do this. They're not going to get to try again if they fail, right? So if they fail, they fail, and you don't get the randomness. But we're going to try to assume or use this protocol in a place where they have an incentive to succeed, right? And we observed that if you do that, then the initiator can pick these subgroups so that nobody needs to trust the output of the randomness if the initiator no matter how the initiator picks them. There's no way the initiator will be able to bias or change the randomness if it works correctly, or if it successfully finishes. On the other hand, of course, the initiator might just fail to complete the protocol, but we're allowing that to happen. Now, so this gets us. It turns out this gets us part of the way there. It gets us scalable randomness that guarantees that an initiator who actually wants the protocol to succeed can ensure that it will, but it doesn't give us a beacon. What we want is a beacon that we can know will run on its own, at least once it's started, without depending on anyone and without anybody being able to stop it. And that's what RandHerd does. RandHerd uses RandHound as a bootstrap protocol. It doesn't rely on the RandHound generated randomness to do anything but provide setup, so that if the setup works, then we know we've got a working beacon, and then we can trust the subsequent output of the beacon. If it doesn't work, then we're going to use a Byzantine fault tolerance style leader election protocol to pick someone else who will try in their turn to initiate the beacon and launch it, right? And so basically, we showed that using this combination of bootstrapping techniques, we can scale these types of Shamir secret sharing threshold randomness protocols. We can scale them as much as we need to. We can scale them to thousands. If we had a bigger test bed, I'm confident we could have scaled to 10,000 or more, right? And this scales orders of magnitude better than protocols that that just use Shamir secret sharing, right? Okay, so that's all I'm going to say, and I know I'm running out of time. That's basically all I want to say about this research background. And like I said earlier, there's a lot of other interesting and important research background in this space as well. I instead want to move right to DRAND. And what is DRAND? I'm not going to say much about it now, but basically DRAND is a protocol that was initially started within the DDIS lab, especially under the leadership of Nicolas Gailly, who will be talking later. And DRAND basically recognized that we need something much more simple, but for deployability, but at least for now, DRAND doesn't need to scale to thousands of nodes because the League of Entropy doesn't yet have thousands of members. Maybe, hopefully soon it will. And maybe then we will need the scalability techniques that Randhound and Randherd prototyped. But until then, for now, we needed a simpler, more streamlined, more operational protocol for deployment. And that is what DRAND is. Now, I'm not going to get into the details of DRAND because I don't want to steal the thunder of the later speakers. So I will just conclude with the basic takeaway points of this talk. Threshold public randomness is a very basic, important primitive. To do it right, you need something like, in this threshold model, you need something like Shamir secret sharing. Randhound and Randherd showed how this can scale as much as we need it to, but then the League of Entropy is taking over and making it practical and usable as an internet utility now. So thank you very much for your attention, and enjoy the rest of the event.
Thank you to Bryan Ford for giving us a solid grounding in distributed randomness fundamentals for the rest of the conference. I particularly enjoyed this explanation of Shamir secret sharing. Never send Muppets to get your treasure, I think is the takeaway there. Please remember that if you have any questions for Bryan, you can type them right now in the Zoom chat and in the event's Telegram channel, and we'll get them ready for the Q&A. And now we'll move on to our next speaker. Our next speaker, Vitalik Buterin, is a co-founder and inventor of Ethereum and helps to lead the Ethereum Foundation. His interest in distributed systems was kindled by a harrowing experience of spell nerfing on a centralized World of Warcraft server. We are delighted to have Vitalik with us to talk about Ethereum 2.0 and its usage of the beacon chain and why randomness is critical. Now let's all please welcome him to the stage.
Thank you. Hello. All right. So can everyone hear me okay, by the way?
Okay, I'm so sorry. I was giving a lecture as you saw. Sorry about that. I didn't realize you.
Should I start?
Yes.
Yes, I should.
Yes, you should.
Okay. So great. I'm going to just share my screen now and start talking about randomness. So randomness in the ETH2 beacon chain. Right. So I guess to start off, I'll talk a bit about kind of what is randomness good for in the context of blockchains in general. And there's probably two major categories of use case here. So there's a protocol layer, and the protocol layer randomness is generally useful in the context of proof of stake. basically because proof of work kind of contains its own sort of built-in unpredictability in terms of selecting and kind of who chooses or who gets to create each block. But proof of stake doesn't have that kind of computational mechanism, and so you need some kind of randomness for choosing who gets to propose which block in a proof of stake system. And in the context of both proof of stake and sharding, kind of committee selection. So whenever you need to randomly sample some number of validators from a much larger set, you need some form of randomness. There's also application layer randomness. Application layer random sampling, so like for example, augur voting, fraud-proof lotteries, basically, and in addition to that, other games. So any kind of game that depends in any way on a random chance, you need, and where you want that game to run on the blockchain, either because it controls so kind of the outcome of the game controls some assets, or just because like you want to have a game on the blockchain to kind of make the thing more trustless, then you need on-chain randomness of some kind. Now, what properties do we want, right? So clearly, on-chain randomness can't be truly a kind of random in the mathematical sense of the word. It has to be a deterministic function because we need consensus on the output, right? It's a blockchain, we need consensus on every bit of the state, and if the randomness gets used by the blockchain, well, that's going to be part of the state. What we want is unpredictability, right? We want the number such that it's not possible to predict that number all the way right up until the moment that that number is released. Now, the main problem in these randomness designs is this kind of last manipulator problem, or I call it last mover advantage. So the idea is that there has to be some last actor that triggers the action that basically causes the state change that kind of goes from people not knowing what or the chain not knowing what the random result is to the chain knowing what the random result is. And this last actor basically inevitably knows that result first. And so they have this kind of manipulation vulnerability where they can choose to either publish that data or not publish it. And this potentially gives them a kind of the ability to manipulate the result, at least to a small extent. And so the question is basically, how do we kind of solve that problem? Early scheme, RANDAO. So this is something that has existed for quite a few years now. The basic idea is that you have some set of participants. Each participant in a kind of first round first publishes the hash of their seed, and then in the second round publishes their seed itself. And the seed that they publish kind of gets checked against the hash that they publish, and so in the second round, the decisions that each participant has, there's basically only one decision, right? To publish or not to publish. And the result of the RANDAO is basically, you take all of the results or all of the seeds that get published, and kind of you add them or XOR them or whatever together, right? So it's fairly simple. There's a natural extension where if you want your hash commitments to be reusable, instead of using hashes, you commit to BLS pub keys, and then you basically kind of multiply the corresponding private key by or rather you use the corresponding private key to just sign a message consisting of different epoch numbers, and BLS signatures have the property that there's exactly one valid signature for every given message, and so you can use that as a kind of a kind of commitment that you can just keep on opening in different ways over and over again for different rounds, but the mechanism is the same, right? So there it is in kind of 3 lines. The main problem here is, of course, kind of you have these actors V1 to Vn, they publish the hashes and then they publish the values, but what if the last actor Vn never publishes Xn, right? The result is this, but what happens if the last actor never publishes Xn? And we can think about it in the context of, say, some kind of lottery, right? And imagine that one of the participants in this lottery also is actor Vn, and actor Vn sees X1 all the way up to Xn minus 1, then they see Xn, that's because they generate it, but they see that with XN the result is unfavorable to them, right? So what they would do is they just like drop offline in their capacity as a RANDAO participant and just never publish XN. So how do we prevent this? The obvious answer is that VN never gets the reward and probably loses part of their deposit. The penalty probably can't be too high unless we allow a really long 1 week delay, basically because, well, if a VN never published XN, it could be because VN got censored. There could have been an attack on the chain. There could have been a DOS attack on VN or whatever. So there is a cap on how high the penalty can be to VN. But so in general, we can say kind of this actor VN has a 1 bit of manipulation power. They can either publish XN or they cannot publish XN. And if they don't publish XN, then, you know, presumably you'd have to start the mechanism again with a new set of actors. And this is at some medium cost. This is often good enough, right? So ETH2 phase 0 uses this mechanism, except it's done in this more kind of streamlined way where you have a whole bunch of validators, and every block proposer kind of basically does a RANDAO reveal as part of publishing a block. So instead of it being a kind of discrete in rounds, there's just this seed that constantly gets updated. And this is good enough for us because we need randomness seeds for some specific use cases. And there's only 2 requirements, which is 1, there can't be too much space for manipulation. So having 1 bit of manipulation power is fine, but having, you know, like 30 bits of manipulation power would be too much. And the reason for that is because for a committee selection, like for committees to be secure, it's okay to allow the committees to be kind of re-randomized a few times, but if you allow the attacker to just keep on grinding until they find a committee that's maximally favorable to them out of billions of possibilities, then potentially the kind of the safe committee size that you need to make sure the attacker can't take that over would increase by, you know, like maybe something like 40 or 50, right? So it would just cut down efficiency for us quite significantly. And then the second requirement is that manipulation should be more costly than the reward, right? So like, for example, if we're using randomness for committee selection and for block proposing, then if you can manipulate the randomness by 1 bit, then you can exercise, like, I think it's either 1 standard deviation or like, so I'm sure some mathematician could correct me, like O of 1 standard deviations, basically, in terms of kind of how many or how many more kind of positions you can give yourself in a particular committee. Now, of course, in ETH2, kind of we use this shuffling mechanism, so everyone's always in exactly 1 committee. But, you know, if you care about being in some committee more than being in other committees, plus the opportunity to propose a block. But in order to get these things, like, you have to make a guaranteed sacrifice of the reward for proposing a block right now, right? And so basically this is never worth it, right? Or is at least almost never worth it is the idea. More advanced randomness algorithms. So Ido Bentov came up with a lot of this. Instead of using this kind of commit reveal where everyone publishes data, you would, and then you XOR it, basically n actors each commit and reveal to 1 bit, and then the output is the majority. So if more actors reveal 1, the output's a 1. If more actors reveal 0, the output's a 0. On average, requires square root of n actors to fail to reveal. So basically, you need square root of n participants to kind of on-chain appear online to manipulate the mechanism. The downside is that if an attacker does control that much, they can attack reliably as opposed to just attacking 1 over square root of n of the time. So this is one way to kind of make an attack more expensive. We're not using this just because the kind of complexity increase is not worth it. Now, instead, we are, when ready, going to augment the RANDAO with verifiable delay functions. Yay! So quick recap of a VDFs, basically a function f of x equals y with the properties that, first of all, if you have x, anyone can compute y. Computing Y requires a large minimum amount of sequential computation and beyond some points cannot be parallelized. And given Y, you can easily verify that it's the correct output, or alternatively, like you might need a witness, but you get basically the same effect. Example of almost a VDF. Just repeatedly hash a number, right? You take X, you hash it once, you hash it again, you hash it again, you keep hashing it a whole bunch of millions of times. It's clear how to compute it. It's not parallelizable, but it's not easy to verify except by rerunning the function, right? So verifying is as expensive as computing. Slightly better example, inverse MIMC. So it's actually better to think about inverse MIMC by first talking about the inverse of inverse MIMC, which is regular MIMC. So start with a number, add a key, cube it, add another key, cube it, add another key, cube it, and so on and so forth. And the inverse of this, of course, is to start at the end, subtract, cube root, subtract, cube root, subtract, cube root, subtract. So like here we have it, right? Subtract, cube root, subtract, cube root. And this is modular cube rooting, right? So it's mapping 0 to p minus 1 to the set 0 to p minus 1. This is all done kind of modulo p. Cubing is much faster than cube rooting. It's basically about the speed increase is about the same as of the number of bits in your field. So with say in a reasonable size field, the verifier could have a 100x advantage, or this could go even higher. So the idea would be that to compute the VDF, you would use this cube rooting function, and to verify it, instead of doing it forwards, verifying can be done by running the computation backwards. And there's an extension, which is the prover runs it forwards, and then the prover also runs it backwards, but then the prover makes a snark or a stark of running it backwards. And then you can definitely verify the snark or the stark quickly. So this is one path, and it's probably the easiest of the VDFs to understand. But there's also other VDFs. There's the repeated squaring based ones. There's a lot of these functions. The Ethereum Foundation has a VDF and an ASIC project that we've talked about. So a lot of research going into this area, which is great. So why do we care about VDFs, right? Basically, we care about VDFs because we want to get rid of last mover advantage. So if one actor disappears, then someone else can compute the same function and they can get the same results, right? There's no kind of individual participant specific secrets that are getting released. And so there's no individual participant that the outcome kind of hinges on. Those with better hardware can, to a limited extent, learn the answer earlier than others, and this is a kind of challenge, and I'll talk about this. Need hardware analysis to determine kind of how long it takes to answer. But you can do a kind of crypto-economic game, right? You can kind of on-chain publish bounties for computing VDF outputs as quickly as possible, and thereby you can at least kind of have the system learn how quickly function can be computed with kind of public hardware. So randomness in the beacon chain, this is part of the kind of ETH2 annotated spec that I've been working on recently. So the idea is that the blockchain kind of proceeds in slots, and there exists this kind of RANDAO. So this is a kind of constant ongoing RANDAO where every slot someone reveals a commitment, and then that gets kind of XORed in, reveal a commitment, XORed in. And the RANDAO mix for one particular slot then gets used as the seed for a kind of 32 slots into the future. And we deliberately provide this look ahead of 32 slots, basically because we want to give people some warning time so that even over here, they basically know what responsibilities they're going to have 32 slots, which is about 6 minutes into the future, so that they can, join the right P2P subnetworks, do some other calculations, like basically just prepare for whatever their responsibility is going to be. So this is the status quo, right? It's basically just a RANDAO where the output of that RANDAO goes into generating a seed, and then that seed goes into kind of random selection, and then combine that with the validator set, and you sample block proposers, and you sample all of these committees. We plan to kind of insert the VDF here, right? So instead of the RANDAO mix being the input for the seed, the VDF of the RANDAO mix is the input for the seed. Now, we will have to extend this from one epoch to kind of many more epochs. And this is why, right? basically, so we assume that the attacker has some kind of advantage, right? Like basically, there's some speed at which you can compute the VDF with public hardware, and the attacker can compute the VDF kind of n times faster than everyone else. So n could be, I know people have different opinions. Some say 1.1, some say 4, some say 30, some say like 100. In the Ethereum team, we're definitely on the conservative side. Now, there's two attacks that you can use if you have an advantage, right? One attack is you compute the results within a single slot and use that answer to manipulate the Randall, right? So basically, if you're over here, then as soon as you see what the previous guy's Randall reveal is, and so you see what the previous Randall mix is, you know what your Randall reveal is, and so you know what your Randall mix is. And so if you can quickly compute the VDF within a single slot, then if you like the answer, you can publish your block. If you don't like the answer, you can skip your block. And so we're basically right back to kind of just having a Randall, right? So the reason why we combine a Randall with a VDF is so that even if the VDF breaks, we still have a kind of Randall level of security. So that's the first attack. The second attack is you trick the network into thinking that your hardware is the public hardware, and then you disappear, right? And the idea behind disappearing is basically that after you disappear, kind of the network can't learn the answer in time. So here was a kind of diagram to see what the two attacks are. So right, if you see like this is a kind of single slot duration. So this is when you learn the other people's information that goes into the seed. This is your deadline for publishing. This is the kind of target VDF solution time, and this is the kind of target time for the protocol to learn the solution, because this is where the VDF solution actually gets used, right? And so the idea is that if the network kind of targets the VDF solution being published over here, and by target I just mean the network can kind of adjust what the difficulty of the VDF is, and it can adjust the number of rounds or whatever. So your first attack would be if you have an advantage, then you don't really reveal your hardware, and so the target time gets set based on not having your hardware, and then you use your hardware to compute it quickly, or alternatively you use your hardware and then you suddenly disappear, and the network just then doesn't have the ability to use a VDF output all the way up until kind of over here, right? So basically the problem, the challenge is then that kind of T use, so this minus kind of T start, this kind of difference in time between kind of the start of computing the VDF and using it needs to be the slot duration multiplied by kind of the attacker advantage squared. And that would basically motivate kind of why when we had the VDF, instead of using the Randall mix from one epoch ago, it would be the Randall mix from kind of quite a bit further back. So the use of the Randall and the VDF in ETH2. So the Randall will be used as an input into the seed. So the seed is kind of a hash that gets used to randomly select the proposer of blocks in the beacon chain and the shards in all of the different kind of functions. And it will also be used for committee selection, right? It'll be used for choosing these kind of random subsets of validators that get assigned to a particular responsibility to kind of verify and attest to a particular block. And then the VDF will also be accessible to the application layer as a randomness utility, right? So one nice thing about application layer use cases actually is that for a lot of application layer use cases, kind of you don't need this hard deadline. And so like for a lottery, for example, right, you can just have the answer whenever you have it. And so from a lottery's point of view, you can basically the time between request and the time between use actually is going to be here, right? But for these consensus layer applications, we do need to have a fixed time at which the answer actually gets used, and so there's this kind of advantage squared problem. So yeah, and that's kind of roughly how Randall works, how VDFs work, how we plan to actually use the two in the Ethereum protocol, and kind of what the use cases are for us. So thank you.
Thank you very much, Todd, for a great talk on the importance of randomness in the beacon chain and the use of the RANDAO and the VDF in ETH2. Please remember to post your questions for Vitalik in the Zoom chat and in the event's Telegram channel. Next up, we have a tag team talk from Protocol Labs. On the top rope is Juan Benet, founder and CEO of Protocol Labs, an open source research and deployment organization building next generation web technologies. Outside of the ring, holding folding chair, is Irene Giacomelli, a research scientist in the crypto lab of Protocol Labs research, focused on Filecoin research. Juan and Irene are going to walk us through why Filecoin, a decentralized storage network designed to store humanity's most important information, decided to use Drand as its source of randomness. Now let's all please welcome Juan and Irene to the stage.
Hello, great to see everyone. I'm going to be sharing my screen. Hopefully you can see that. Is that all good? Great. We're here to talk to you about why Drand is going to be used in the Filecoin network. The internet is made up of a number of very important public utilities, which are effectively large-scale distributed systems that are organized by protocols. These protocols can be are often created by a small group of people that notice a problem. They design a system, they talk about it, they build prototypes, they test them, they improve them, and eventually these protocols get turned into specs, submitted to the IETF, and they become part of the large network of systems that all work together to give us the functionalities that we use every day through our computers. So over time, we have a large compendium, accumulating compendium of protocols that make up all of the interactions that we have online. So right now, as we speak in this moment, there are probably hundreds of protocols in use at the same time by all our machines. So the story of time is interesting. Around 35 years ago, the internet needed a way to tell time. There were a lot of different computers around the network that had a very large clock skew, and so people needed the ability to synchronize the clocks of all of these computers. And so people decided to build an internet protocol to do this. They built a distributed system to synchronize distributed clocks and provide a publicly available network-wide clock, trying to reduce the skew, trying to provide access to much better clocks, and so on. NTP, the system they built, the network time protocol, grew and grew, and nowadays powers all of the time and all of the clocks that are synchronized over the internet, including our computers, get our time from this protocol and these systems. NTP nowadays is hooked up to atomic clocks that measure the time extremely precisely and can give us an extremely good notion of time. But this system was built over time by having a kind of a core set of parties that would have access to kind of a effectively trusted sense of time, and they would and there was a protocol designed to be able to ask those parties for what time their clock read, and then a larger network of sort of relayers, which are these different strata, enabled that clock to kind of spread out across the internet. You don't want to enable all parties to request time from a few nodes, and so this relaying architecture served to distribute and disseminate that information. So today, the internet needs a way to get randomness. So the story is very similar. We need a foundational internet protocol like Entropy to create a verifiable, unpredictable, and unbiased randomness source. And this randomness source should be publicly available anywhere in the world. And so it's a very similar problem to NTP, where you want a set of parties working together to produce randomness, and then you want to distribute that randomness as far and wide as possible and enable all parties in the network to access it. So that's we'll hear a lot more about how DRAN works later on, but that's effectively a similar structure here, where there are a set of DRAN nodes, and there are some DRAN relays that can spread out the information across the network, and eventually clients use the time from that that comes from the source DRAN nodes in their applications. And so DRAN is designed to be this very concrete and concise protocol to just do that, and therefore it can become a foundational internet protocol for randomness. So the hope here, and one of the big reasons that we at Protocol Labs and in the Filecoin project saw an enormous amount of potential in DRAN is that it's designed to enable us to build a large public utility like NTP, like DNS, like all of the other protocols that we use day to day, and provide a randomness service everywhere in the world, and work together to achieve that service. And I think that and so these kinds of protocols tend to, the open innovation of the internet, the ability for people to come together, find a problem, design a system to solve that problem, create a protocol, implement that protocol, and get it built into a foundational system, and then kind of propose to the rest of the world to use that system. That kind of permissionless innovation is fundamental to how the internet has become so successful. It is one of the great triumphs of the internet as a large project for all of humanity. The ability to upgrade the network, upgrade the systems that we use permissionlessly as a group coming together, building something, testing it out, making sure it works. And once it gets better and better for all kinds of use cases, then it sort of gets promoted into this kind of public utility that everybody in the world can rely on. So that's our hope for DRAN. We think that it is time that the network gets a proper, secure randomness protocol that's distributed everywhere, and we think that DRAN is a great has a great shot to become that protocol. Of course, randomness beacons over time will change. We'll find better ways of doing things, and perhaps DRAN over time will adapt to incorporate those things. Who knows? This is just the beginning for the long term of DRAN. These protocols, things like NTP and so on, are decades old, and they've gone through all kinds of upgrades. Now, I think that blockchains have a unique opportunity to serve as the systems that cause this network-wide randomness source to appear, because many other applications can deal with private randomness or some kind of public randomness that's very use case specific or something like that. But blockchains are decentralized networks that require a lot of parties to come together to produce to again form some kind of system that provides a service. And randomness is critical for all kinds of things in blockchains. There are things it's critical for consensus in elections and sortation-based protocols, things like proof of stake and so on. It's also needed for all kinds of proof protocols and actual cryptographic protocols that need to run as part of various blockchains or applications in a blockchain. And it's also pretty important to get randomness into things like smart contracts and so on, where you can have all kinds of applications that need access to a trusted or not trusted, but they need access to an unbiasable and verifiable source of randomness. Actual elections, so beyond the kind of computer protocol elections, but rather human elections also need a really good source of randomness. So I think that blockchains the blockchain communities can afford to develop this protocol and turn it into a foundational source of randomness for the world. And so one of the things though is that if you start if you make a blockchain sort of depend on another protocol, then you enter into a world where you have one system that is supposed to be have very high availability and always run and so on, suddenly depend on another chain. And so if you think about sort of how DRAN produces randomness over time, we'll hear a lot more about how that works later on. Then you would have kind of a blockchain following that protocol. And a lot of people, this would give a lot of people pause in terms of making a blockchain dependent on another protocol. But in a way, that's exactly where all of the sharding proposals are going. So blockchains in general, as we scale them up to get better transaction throughputs, are gonna end up in this world where there's an architecture with many different chains, and there's a sort of potentially hierarchy or something like that that achieves scalability. So in that sense, you can think of randomness as just one of the root chains. And effectively, this is kind of where Ethereum has arrived after considering many different sharding proposals. Now the current goal set and the beacon chain that is I believe now live, and which is really awesome, now uses this beacon chain with that generates randomness securely. And this is an extremely complex problem, as we heard from Vitalik and we've seen in the community. So this is I think a great example of how we can build blockchain systems that depend on this kind of source component for randomness. So in Filecoin, it kind of, another way to draw it, it's very similar to the Ethereum 2 approach, and in Filecoin uses Drand in this way where there's effectively the Drand protocol is producing a chain of randomness, and then Filecoin sort of pulls the randomness into it. We'll hear a lot more about how exactly that works from Irene in a little bit. So we hope that by us using Drand, we will give a lot of momentum to Drand, and we hope that will also inspire other folks to come and work together on this foundational protocol. And then whether it turns out to be Drand or maybe a VDF-based thing in the future or something else later on, our goal and our hope would be that all the work that we're doing for building these protocols can turn out to produce a proper foundational public utility in the internet that everyone can rely on for randomness. So I'll give a short introduction to what Filecoin is, and then I'll turn it over to Irene. Filecoin is a decentralized storage network designed to store humanity's most important information, and we want to build a very large-scale network with vast storage resources that's decentralized and organized by a protocol alone, without having to involve sort of humans in the loop in the loop of making a deal. That's of course extremely difficult, and you can get close. And you can think of the system as producing this market where on one side people are coming in to provide a storage supply, and you can see pictures of Filecoin miners setting up their racks and machines and so on. People come together to provide the storage supply, and on the other side you can have applications and clients and so on consuming that storage resource and using it. And so Filecoin is a blockchain that organizes this storage marketplace. And so you can think of a large constellation of parties that all come together to make this thing work, from all of the hundreds of miners and hundreds of different organizations working together to produce this system, and then the many other organizations that build different parts and pieces of the protocol, plus then all of the end users that are going to consume all that information and use that storage supply. All of these people, all of these organizations and so on depend on a good and secure source of randomness. And so all of it is all of these folks will make use of what you'll hear about in a moment. So I'll turn it over to Irene.
Thank you. Let me share my screen. Can you see it? Okay, so thank you for the introduction. I'll take from here and try to, add some more details about how Filecoin works, and hopefully these details will help you to understand why randomness is so important, and especially why we choose to go with the random beacon, with the as a random beacon as source of randomness in Filecoin. And as Juan said, so Filecoin is a blockchain where miners actually need to provide storage to participate in this Filecoin chain, and they will earn from the consensus for participating from the consensus protocol that extend the chain, and they will earn some Filecoin tokens. More precisely, the storage that is provided by the miners is divided in units that we call sectors. You can think like one sector is this specific amount of space that the miner is committing to the network. And these sectors containers for data, but you cannot just put data in the raw form. We need to encode the data with a specific protocol, we call it proof of replication, that basically from data creates a replica, and a replica has some very special property that we are key for Filecoin. For example, a replica is not compressible, and a replica enforces unique storage resources, and a replica is not easy at all to regenerate, to reconstruct. Once we have this sector with replicas, each miner has its own sectors. Basically, we ask miners to periodically prove that they're still storing the replicas, because in Filecoin, we are interested not just at storage, but storage through time, okay, useful storage. And this is very easy. I'll mention this post proof of space-time in the following. Remember that for each replica, the miner stored the replica and put on the chain just the root of a Merkle tree constructed on the replica. When we ask to the miner to prove that it's still storing consistently, persistently over time this replica, it just has to open path for random location in the replica, open the path respect to the roots that everyone knows. And this, because of how the replica is this special encoding with special property, basically guarantees that the miner is storing now, and it has stored through time since the last time we asked him to prove, basically. Okay, this is the situation, and these are the building blocks. And clearly, with these building blocks, we can construct Filecoin if we have good randomness, because we use randomness a bit everywhere. We use randomness in leader election and consensus. We use randomness to check that the replicas are constructed in a correct way. We use randomness for this post proof of space-time. I don't have time to explain everything, so I focus on the consensus part. How do we use it for leader election? And leader election, in general, this means that we have a set of participants. They all have different power, different weight, and we must find a way to select a few of them in a way that is verifiable. They can prove that are the ones that have been selected. They are selected, the more power you have, the more likely you are going to be selected, the fairness properties. And we want to be secret, so I am the only one that I know I'm being selected before I reveal it. And in particular, we also want, for scalability reasons, some efficient protocol, like hopefully with no communication between the participants. In Filecoin, a leader election has two steps. So first one is kind of a standard step, like a VRF-based election. I will explain it a bit more in a second. And then we have a winning post. So we do one of these proof of storage through time for the leaders that have been newly elected. VRF-based election is, I would say, a standard tool for blockchain, and means that you have like this verifiable function that is just basically a pseudo-random generator that will also take a key, an input. A key takes a seed, as all the pseudo-random generator. A good seed, it also takes a key, and the output is the pseudo-random number, and also a proof that particular number, I call it S in the slide, is correctly computed given that key, and everyone can check this. So when you use a VRF, leader election is quite simple. Construct an efficient leader election is quite simple because you associate miners with keys, and then you just, every miner runs locally the key on the seed and check if wins, check this random output against a target that it has to be proportional to his own power. That is a public information, everyone can check it. And this way you get the fairness property, okay, because the larger the target, the more likely that you win. And also from the property of the VDF, you get all the other properties that you need from this leader election. Be careful that we do need a good seed, a good fresh public random seed for each leader election, okay? But given that we are done, the second step, this is very particular, this is very specific to Filecoin, is that we are not happy to just let leader with the VDF. We want to leader to prove that they still have their replicas, okay? And what we do is, for example, we ask to, we sample the chain, somehow samples at random, one of the sector they claim to they are still storing, and they do a post for that specific set. We call this the winning post, the post for the miners that are winning the leader election. And here again, it's very important when we sample, we do use some source of randomness, so a seed. So as you see, as you see, everything works out quite well, assuming that you have this magic box that is, my slide is a green box, that produce these seeds that has to be unbiasable. Otherwise, people can win more, can break the fairness property. It has to be public for variability and distributed also because Juan motivated this very well. And also, something that is very important in Filecoin is unpredictability of these seeds. Otherwise, if you don't have unpredictability, the post becomes somehow ineffective. Let me explain this why. Assume that you are a miner, you are storing your, you are a miner, you are participating in Filecoin, and you are on average elected, I don't know, once or twice a day, not very often. And assume also that the seeds comes a bit in advance. I don't know, 1 hour, 2 hours in advance. So the seeds that they're using now for knowing if you are elected with them now, you know it 2 hours before. If this is the case, what you can do, you could delete your replicas for like all the times that you know you're not going to be elected either, and just redo the replication algorithm just before or in time before the election. So unpredictability, keep this in mind, is essential to guarantee persistent storage, to guarantee that when we check persistent storage, this check is effective. So now we want to understand how we spend time to understand how we can get these seeds. And like, I guess the first normal place to look is the blockchain itself. You have a blockchain, people are using this for producing randomness, so that's exactly what we did. We try to use the blockchain itself to see if we can extract this small seed and use it for the goals I show you. There are protocols that do this. Usually this protocol, they kind of extract the seed using information that is created and stored in blocks that are in the past of my blockchain. If you're familiar, like Ouroboros browse, spacing, they do something like this. So you take, very quick example, you take some headers from back in the past in the chain when the chain is stable, and you hash together, and you use this as a seed. This works, it gives you randomness that is not easy to bias, depends clearly on the protocol, but the problem is that it is predictable. It's very predictable because you have to take something that is from the past. So it means that it's something that you are going to know in advance, okay? So it doesn't work for Filecoin, this solution. So the natural next try, the next attempt is, okay, do the same extraction or something similar with information that are in recent blocks, like blocks that are not back in the past, like much before finality, like few epochs before now. And the problem with that, as Bryan also mentioned in the first talk, is that then it becomes very, very easy to bias. Because basically the chain is not stable now, I can just, maybe one miner can just not append his own block, producing his own block, and do a lot of these let's call it short local attack and bias to the next seed, okay? So we kind of lose the biasability property that is also indispensable. So basically, Warren, if you try to extract from chain, we have this standoff, we saw this standoff where if you try to take something that is unpredictable, then you give up biasability and the other way around. So the solution, a smart solution that we came up is to use a random beacon. So give up with extracting from chain and use these external good sources of randomness that is has all the property that we require, and this solves our problem. And clearly, I mean, I don't have to repeat this because one motivated is Drand was the good choice for us for all the reasons that he mentioned. And with this is all. I hope you understood the challenges that we faced and we solved it with thanks to Drand. And happy to take question later or now, I think.
Thank you. Thank you very much for a great talk on how blockchains can motivate building a foundational randomness protocol. And congratulations for picking Drand as the randomness beacon for Filecoin, making it the first production service relying on the League of Entropy mainnet. Remember, you can still drop your questions for Juan and Irene in the Zoom chat and in the Telegram channel, and they'll get to them in the Q&A, which is coming up next. So I think all the speakers have gathered. Thank you to all the speakers from our first block of talks, Bryan, Vitalik, Irene, and Juan, for setting the stage for a great Q&A. We'd like to invite everybody to continue to participate in the question and answer session via the chat streams in the Zoom webinar and Telegram channel. Your discussion might spark someone else's great question or at least set up a few conference memes. Now let's let the Q&A begin. I think our first question will come from me. It's from Joshua Topkin via Telegram, and he's posing it to Bryan Ford. Bryan, are you with us? You ready?
Yep, I'm here.
The question is, do you think using multi-party computation techniques like threshold signatures among a sampled cohort in order to source a random seed from a chaotic system, like weather data via oracles, can be used for blockchain systems? Is there a place for true randomness in blockchain security? Or are deterministic verifiable random functions, VRFs and VDFs, the only viable options?
Great, thanks. That's actually a really good question. There's a number of issues embedded in that. So of course, there are indeed many ways to do distributed randomness. And Drand, you know, as one point that we haven't gotten to yet, but will come in a later talk. Drand already uses contributions, you know, original contributions from randomness from different sources. Each of the participants can choose to use, you know, subatomic particles or weather data or picture videos of lava lamps or anything they want to produce, you know, really good, high quality, true randomness and feed it in, right? Now, the big caveat, one big caveat in the Drand protocol as it currently stands, using BLS signatures, this true randomness is only coming in once in a while at the basically setup time, and each successive BLS signature is indeed deterministic, you know, deterministically produced from the seed. Now, there are other protocols. In fact, a detail of the Rand-Howd and Rand-Hurd protocols that I didn't mention is actually those, instead of using BLS, they use Schnorr signatures. And in that protocol, there's actually an opportunity. It's a two-phase protocol. It's more complicated, which is why it, you know, wasn't which is why it was less attractive for Drand, and it has other issues. But, you know, one of the nice things about using a two-phase protocol is there's actually an opportunity in every single round for each participant to inject new true randomness if they want to, right? So at the cost of increasing protocol complexity and, you know, and having to give up BLS for a, you know, 2 or more phase Shamir secret sharing protocol, we actually could very well use true randomness in every single round. But, you know, that's an engineering decision, and we would, I think it's worth exploring in the future, whether there should be, you know, a DRAND 2.0 or 3.0 or something that that incorporates true randomness in every single round. And there's many other interesting potential ways to improve it later as well. Okay.
Thank you very much for that comprehensive answer. Remember, you can always follow up in the chat, although not directly to the speaker. The next question will be posed live from Marcel Jakic. And Marcel, are you ready? Are you with us?
Yeah, I'm ready. Can you hear me?
Yes.
Yeah, so hi, Vitalik. The question I was asking, one of the potential solutions for calculating the VDF function to generate randomness are ASICs for efficient calculation. And how would you see that to be a risk for decentralization, so that the ASICs, which are very specialized hardware, centralize Ethereum 2.0 to some extent?
Yeah, good question. And I think, first of all, like ASICs are inevitable, like coming up with a function that where even the sequential speed can't be sped up with ASICs seems to be close to impossible. In terms of the things that we can kind of do to engineer around that reality, I think, first of all, like for example, the Ethereum Foundation is kind of paying for manufacturing these ASICs, and the plan is to kind of try to distribute them as widely as possible. And the ideal would obviously be having an ecosystem where you have multiple manufacturers. And then the other thing is that like if you're really concerned, you can kind of tune up that advantage parameter that I talked about in the presentation, and basically just kind of have longer delays and longer timelines, and make the protocol secure against someone having an ASIC that's even like 30 or 50 times faster than everyone else.
Okay, thank you.
I could add to that a little bit. Yeah, I think we completely agree with Vitalik, and we are also participating in the work to produce this VDF ASIC, and we would love to distribute it as widely as possible. If we can do that, then there shouldn't be a concern about access to ASICs. If we can get a large network of parties making them, if we can distribute them widely, if they can be cheap enough, if they can be very close to the physical limit, then I think we'll all be much better off by having VDF hardware like that, and we're working together to make it a reality.
Maybe follow up, wouldn't the extent of using ASICs also again increase resource consumption, which is proof of stake consensus trying to combat?
It would, but you only need a few people computing the VDF, and so the resource consumption is probably bounded above somewhere in the low millions of dollars.
Still like a lot less than as it is today in proof of work.
Like there's no kind of way to compute a VDF much faster if you put lots and lots of money into it. So it's not like it's like a race where everyone just like keeps on throwing huge amounts of capital in.
Okay.
Thank you. We'll move on to the next question, which is from the chat, and it's directed at Juan and Irene. How do you see Filecoin's randomness needs evolving? Do you expect the random beacon currently provided by Drand to be sufficient in the long term, or will it need to evolve as well?
That's a great question. And it really depends on how Drand itself evolves too. So we know that eventually Filecoin will follow in Ethereum's footsteps and get to some sort of sharding solution as well. We might just use the same one, we'll see. And we know that we will have different randomness needs, and perhaps the block times might go faster and so on. There's a lot of different kinds of engineering challenges that change once you target a properly sharded network. So we think, for example, one interesting thing might be that you might want to have shards that move faster, that are geolocated in some part of the network that can have a much faster block time, say sub-second, and if you achieve something like that in one small locality of the world, then you'll need a randomness source that actually can give you something like that. So we would need to think about how Drand might evolve for that. Or potentially Drand itself might evolve to incorporate things like VDFs. So we might see new generation, as Bryan is saying, maybe Drand 4.0 or 5.0, go and use VDFs itself in the protocol once these are widely distributed and used, right? So we're sort of hoping that we can build our work here with Drand and the legal entropy and so on can serve as the foundation for this, protocol, internet randomness protocol that can be a public utility. And whatever the solution is to that problem, we should just kind of keep upgrading the system over time to provide good and high quality randomness.
Great, thank you. The next question is also from the chat.
Can I add just one quick? Sorry
sure.
to interrupt. Yeah, I think it's a great question, and I think it's hard to say. It's basically almost impossible to say because it depends on a lot of things. VDF was mentioned by Juan. It also depends on how POREP, proof of replication, and proof of space-time research evolves. This is quite new. So the things that we have now are based on this time assumption. It's very important to have randomness and predictable. This could change. It's a really new field. So maybe that's another aspect that it makes it very hard to predict the answer. It's give a good answer now.
Great, thanks for adding on to that. The next question is from Telegram from Ilya Sharabokov, and it's directed at Bryan. And Ilya asks, is there a post-quantum analog for BLS RSA signatures in terms of uniqueness properties for DRAN-like beacons? Maybe at least the most promising approaches for that use case. For example, using lattices, isogenies, etc.
Yeah, that's actually a really good question. And unfortunately, I'm not the best person to answer that question because I'm not an expert on that, post-quantum public key cryptography, which is essential for that. My understanding is that all of the post-quantum cryptography approaches to cryptography, some of them might be able to provide the tools we need, but they're immature. I don't yet know of a way to use lattice crypto or these other schemes in the way we need to do this using true randomness. Now, there probably is a way. I think these new crypto systems probably just need time to mature. An expert on, a true state-of-the-art expert on these post-quantum systems might already know of ways, might already be working on them. I'm not sure. But yeah, it's a very important need for future work where I'm sure the problem will be solved, but to my knowledge, it's not solved yet.
Thank you. That shy means that we have time for just a few more questions. And I will take another one from the chat. This one is directed at Vitalik. Does adding VDFs reintroduce some kind of the dynamics present in proof of work? Is it that people need to do an expensive long computation to move the chain forward?
Right. So I think as I kind of said a bit before, like the difference between VDFs and proof of work is that in proof of work, you can just always keep computing the function faster if you throw more money at it. And it is kind of a race, and it's also vulnerable to a 51% attack. So if an attacker does 51% of the proof of work, then you're kind of screwed. Whereas in a VDF, there's like with increasing money, there's only a very limited amount by which you can speed up the calculation, and there's no there's no need for kind of anyone to beat out the attacker. You just have to, and if the public just have to have a computation speed that's within a factor of n of the attacker. Basically the rewards for VDF computation can be set to be much lower, and kind of the amount of economic activity around the VDF is probably going to be much lower than it will be in mining, or than it was for mining.
Thank you. The next question, also from the chat, is for Juan and Irene. The question is, by choosing DRAND, you're introducing a dependency on an external service. Does that make Filecoin less resilient or more centralized?
That's a great question. Like I was saying in the talk, the way the charting is, so let me address kind of the interdependence question. The way that sharding of blockchains is going is that most of these systems and most of these chains there will be kind of a dependency structure between a number of different systems. This is already the case in terms of dependence on the underlying internet protocols. Just people don't tend to think of it that way. All blockchains depend on BGP achieving good routing propagation through the internet. All blockchains depend on the ability to send messages to each other and so on. So we hope that randomness can just become this foundational protocol, just like BGP, just like DNS, and just like these other systems, that is just sort of fundamental and expected as part of the internet. And it isn't seen as sort of like this kind of additional dependency. Now there's a lot of work to get from here to there over time, and more parties need to get involved. It needs to we have to run the network for a very long time with very little to no downtime and so on. And we have to prove out all of the engineering challenges of actually running a network like that. But we hope that that's not going to be seen in the future. It's just going to disappear from slides because everyone will just assume that, of course, you have access to randomness, just like, of course, you have access to routing on the internet. That's just sort of a basic expectation. Now, the other question around centralization, think of the proof of work world where there are effectively very few large-scale mining pools. There are some networks that are very large that have on the order of 5 to 6 parties that together could collude and mount an attack. The Drand network itself has many more parties than that, and we hope that over time that the League of Entropy would expand with more and more parties. So the Drand network itself wouldn't be seen as, or we don't think it's centralized at this point, but there are a lot of different parties working together to produce it. And in the future, it'll get even more decentralized as more partners combine. And if you're worried about centralization in the League of Entropy, you should start up an organization and you should join the League of Entropy and help maintain the randomness. You should be part of the solution.
Okay, great. And on that call to action, we'll move to the next question, which will be asked live by Raul and Chai. Are you with us?
Hi, yes, Roland here. So yeah, to Vitalik for the random, right? So can we use some sort of error correction code to tolerate the no-show of the last actor V in? And also for Ethereum 2.0, will random become part of the native protocol rather than living in a smart contract?
Mm-hmm. So I think the challenge with any kind of secret sharing approach is that in order to actually have those kind of algebraic dependencies between the values that every participant will reveal, you would need to have like some kind of distributed key generation procedure between the participants ahead of time, which adds some complexity. And another kind of annoying thing about it is that it kind of degrades the security model, because it says that even though one participant can't attack the random, it means that if you have k out of n participants, you can potentially attack the system for free. Whereas with a random, you can't attack the system for free unless you have like literally 100% of the participants. So yes, it's going down that path is kind of a complexity increase, and security-wise, like increase in some ways, but decrease in other ways. And like we tend to kind of measure security more in terms of incentives. So the kind of the decreased part, where if you have a majority you can manipulate for free, is definitely a big downside. So basically, for those reasons, like I think VDFs are kind of just a better path to take. And yes, in ETH2, Randall and BVDFs are both going to be a part of the protocol.
Thank you.
Great. Thank you very much for that exciting Q&A session. I think that was pretty thought-provoking, sorry. And I think we're about ready to move on to the second block of talks, which is all about Drand and the League of Entropy. I'd like to thank once again our speakers from Block 1 as we move to Block 2. Okay, hello and welcome again to Block 2, all about Drand and the League of Entropy. Our first two speakers in this segment are repping the League of Entropy, the first production Drand network. Luc Valenta is a computer security and applied cryptography researcher at Cloudflare, one of the biggest networks on the internet, and a founding member of the League of Entropy. Nathan Hamiel is the head of cybersecurity research at Kudelski Security, a provider of cybersecurity solutions and another founding League of Entropy node. They're here to share their perspectives on the past, present, and future of the League of Entropy, the first production Drand network. Let's welcome them to the stage.
Hi there. I guess I'll get my screen presented. Okay, so hi, I'm Luc Valenta. I'm on Cloudflare's research team. And so in this talk, I'll talk a little bit about the inception of the League of Entropy and its founding members, how the project has evolved, and our vision for the future of the Drand and League of Entropy network. So first of all, let's talk about a little bit about why randomness is important. I think you've heard a lot about this over the course of this summit. But applications typically rely on either private randomness or public randomness. So private randomness is secret randomness that a party generates and then forgets about when it's no longer needed. This type of randomness is one of the cornerstones of computer security. And so it's required for key generation, for encryption and authentication. It's required for privacy and anonymity protocols. And basically any cryptographic application you can think of is going to rely on some form of private randomness. And if a faulty random number generator can be devastating to applications that require private randomness. Because even a slight bias in the randomness can be a source of vulnerabilities. So public randomness, on the other hand, also has many applications. So public randomness is random values that are available to everyone to check and verify. So this wouldn't be very good for encryption keys because everybody can see this randomness. So public randomness provides a way to publicly audit randomness used by applications that may have a significant impact. And so this public randomness needs to persist as long as it's needed for the auditing purposes. So one use case would be something like visa lotteries, where they could use public randomness to decide which of a pool of equally qualified applicants is granted entry into a country. It can be used for a secure timestamping service to prove that an action occurred after some time. Clinical trials could use public randomness to split participants into a test and control group in a provably unbiased way. So this could be used to improve the scientific method. For gaming, gamers can no longer blame the RNG for their misfortunes if it publicly verifiable randomness for generating game events. In gambling, there's a high financial motivation to bias the outcome. So for a lottery, so public randomness can be used to provide an unbiased outcome that's publicly verifiable. So you'll hear a lot about other applications for public randomness in this summit. So a public source of randomness should have certain properties for it to be used in practice. So first, it needs to be available. So if the service goes offline, no one can access the randomness, and it's not very good. It should also be unpredictable, so future outputs can't be anticipated, and it should be unbiased. So it should be a uniformly random number. So like Vitalik was talking about with using a blockchain for randomness, it has the problem that the last person to submit the block could potentially tamper and bias the hash of the block, for example, by including or excluding certain values. And finally, public randomness should be verifiable so that any tampering of the output could be detected by a third party. So previously, if you had an application that required a public randomness beacon, the solution would be to use one offered by an individual entity such as NIST. But this comes with a lot of problems. First of all, it's a single point of failure. So in the event of compromise or operational issues, the randomness beacon could go down. And it's also a single point of trust. So not everyone globally is going to be willing to trust the US government to provide their randomness. So that, this leads us to this is where the League of Entropy comes in. So the League of Entropy is an instantiation of the Drand protocol, and it's the internet's first production-ready, decentralized, and verifiable public randomness beacon. So the beacon operators are geographically and geopolitically distributed. The randomness is unpredictable, unbiased, and verifiable. And as an added bonus, all of the nodes use a diverse set of entropy sources to help seed their randomness. So these are the founding members of the League of Entropy. So it started as an experimental network in 2019 to kind of test the Drand protocol, work out any issues that might come up, and so this has been running for about a year now. So now I'll introduce the original members and their entropy sources. So Kudelski Security uses ChaCha-Rand, which is a random number generator that's based on the ChaCha stream cipher. Protocol Labs uses Interplanetary Rand. So this is it's based on the Linux pseudo-random number generator, which relies on environmental noise and randomness from the CPU and other sources. LavaRand, which is Cloudflare's randomness beacon, uses our lava lamps, which are located in our San Francisco headquarters, also behind me in the Zoom screen. So it relies on the chaotic motion of the wax within the lava lamps to generate randomness. University of Chile uses Seismic Rand, which uses randomness derived from seismic events like earthquakes, which I think is really cool. The EPFL's URAND uses computers' local randomness from dev URandom, which is derived from keyboard presses, mouse clicks, network traffic, and other unpredictable events. And the League also has, it also started with 3 individual contributors, as well as these organizations. So that's a little bit about the experimental Drand network, which launched about a year ago and has been running since. But over the past several months, there's been a big push to productionalize this experimental network and make it so this can actually be a critical part of internet infrastructure. So as part of that, we've added a lot of new organizations and universities to the League of Entropy. So in total, the League of Entropy mainnet and testnet have 14 organizations and universities involved now, and we have more joining soon. So as we add more node operators, the guarantees of the public randomness beacon only get stronger. So we really are looking to add new members and definitely invite you to participate. So looking forward into the future, as the League of Entropies move from an experimental network to a production network, the focus has also shifted. So we're a little bit less focused on recruiting members that have these sort of original entropy sources. Although if you have a quantum computer and want to use it for generating quantum randomness, we definitely encourage that. And we're more focused on providing a foundational a piece of foundational internet infrastructure that can be used. So we want to bring on reliable partners that are able to meet the operational security standards of the network. And we're focusing on quality of service, decentralization as well. So Cloudflare's mission is to help build a better internet. So we were really happy to be able to contribute to this project and participate in the Drand network. And we really look forward to continuing to to partner with this network and see it expand. And yeah, because we believe that efforts like this are crucial to the future of the internet. And with that, I can pass the screen over to Nathan from Kudelski Security. Thanks.
Thanks, Luke. Hopefully you're seeing my lovely background on my screen for the moment. All right. Hopefully that's good. I don't know if anybody can still hear me. But all right. I'm going to get kicked off like everybody can see my screen. So somebody please interrupt me if you can't. You've already heard quite a bit about randomness today, as well as about Drand in the League of Entropy. So that kind of covers a lot of the basic points. So what I thought I would do, yes.
Did you mean to share your presentation?
Is it not sharing?
No. Yeah, why don't you try to do that again?
Right. Let's see here, share screen once again. Do that. Do that. I always have to make everything far more complicated than it needs to be, so. Are you seeing it now?
Looks good, yeah.
Okay, good. I couldn't take any more technical difficulties today. So anyway, without repeating myself too much, you've already heard a lot about the need for randomness, different randomness techniques. You've already heard about Drand, you've already heard about the League of Entropy. So what I thought I would do is we kind of talked about the diversity of the League of Entropy. And Kudelski Security is a little bit different than some of the other organizations that are part of the League. So we are a security company. And you know, I think having these diversity of organizations and having diversity in the geographic locations is really good, because the goal is we're trying to create an unbiased, high entropy, random source. And by having these different methods for generating and having it happen throughout the League, it's really good. It's a collaborative effort that leans upon the strengths of the individual organizations, which I think is great. So Luke already discussed some of those. So I'm going to kind of give you kind of this perspective from a security professional / security company side. So this is a picture of me, just in case my video isn't good enough for you. I'm the head of cybersecurity research at Kudelski Security. And it was my team, the cryptographers on my team, that participated in the Drand / League of Entropy project. I have a little bit of a soft spot in my heart for this project, because the actual planning and everything for this happened about a month after I joined Kudelski Security. So I was kind of thrown into it, which is really cool. My team kind of focuses on cutting edge and emerging technologies. And the thing about Drand that was attractive is that it gave us an opportunity to kind of work with, you know, bleeding edge cryptography with a bunch of organizations who are passionate about solving some of the same challenges that we saw as being challenges. And far too often in my career, I've seen a lot of projects / products that were kind of focused on building something cool and then going and finding a problem. That's just not the case with randomness. So I'm also a Black Hat Review Board member. So if you're into the security space, you've probably heard of the Black Hat conferences. I'm the track lead for the AI, machine learning, and data science track. And at Kudelski, we kind of have a similar mission. So Luke mentioned the mission of Cloudflare. Our mission is to help people build better products in general. And that's ones that are safer, more secure, and privacy focused. So we help companies innovate in a secure manner, which then of course builds trust with their customers. And we do this through traditional and non-traditional offerings. So the traditional security offerings are what traditional security companies do, but we also have an innovation group, which the research team is a part of. And we have an advanced lab. So this really gives us a perspective of security issues from the application layer all the way down to the hardware. And one of the things that we do is we help people with cryptography and privacy preserving technologies. So we work with major cryptocurrency organizations, blockchain companies, exchanges, and even companies just looking for secure communication. So that kind of gives us a vision into the breadth of issues that are kind of plaguing the security industry in general, as well as cryptographic implementations. And one of the things that was great about the League of Entropy was working with people, like I mentioned, who are passionate about the same problems. And I've heard quantum mentioned a couple times. We actually have some quantum security capabilities now too. So just like Drand and the League of Entropy is looking at the future, so are we. And we've already heard a bit about randomness. So why randomness? Why choose that as a problem to solve? Well, you know, randomness underpins much of the security in our modern lives. So, and issues with randomness can lead to devastating consequences. So if you think about issues with retrieval of private keys, there's also been an instance where I remember where a smart contract, randomness was exploited in a smart contract to lose about 400 Ether. And randomness typically hides in the background. And we do a ton of audits, and issues with randomness are among the most common issues we identify during audits, and that's from a hardware and a software perspective. So if you think about fairness as well, a lot of the oxygen in the room when you hear about the word fairness is usually related to artificial intelligence. So we talk about bias in historical data sets, and that's a very important topic. But one thing that should also be highlighted is that by using something like Drand that provides a public, verifiable, and unbiased source of randomness, you can create fairness in a publicly visible way. And as far as Kudelski is been involved with the project, we've been involved since the beginning. And Drand aligns with our core research themes. So we have 3 core research themes. That's visibility, simplification, and privacy. 2 of those are painfully obvious. So the visibility, you know, Drand is public. Anybody who wants to request a value can request one. And from a simplification perspective, we've kind of taken the guesswork out of the equation. So it's less opportunities to, you know, create problems in your applications. When we first found out about the LavaRand, we wanted to do something super cool like that because, I mean, obviously using lava lamps for randomness is very cool. So what we tried to do was get a bunch of fish tanks and build an aquarium and then use the bubbles as the chaotic event. But unfortunately, that expense report would not be approved. So we kind of fell back to our using randomness provided by the Cha-Cha scheme. And currently we have 3 mainnet nodes and 1 testnet node. And we've deployed this in a high security environment. So our nodes are monitored 24/7, 365 by our Cyber Fusion Center. So there's a team of people every single moment of the day monitoring these nodes for any kind of intrusion or any kind of tampering, things like that. And I'll keep this brief. So the future, we're excited that the current version of Drand is now you know, available to the public in a non-beta form. We're excited to help bring that vision for the future for something so important. And we look forward to continuing support in the future, whether that be through individual contributions, node hosting, things like that. I want to say once again, thank you to Yolan on my team who put in countless hours on this project. I kind of feel bad, like I'm taking the credit for all of his work. But he put a massive amount of time into this. So I'm glad that his work is finally being realized as well. And we look forward to the future, and we can't wait to see what you do with it and how you put it in your applications and use it. So thank you very much.
Big thanks to Nathan and Luke. It was great to hear from current node operators to get the view from the inside and learn about diversity and entropy. And a big thanks to extend to their teams as well, as Nathan mentioned. Don't forget to post your questions in the Zoom chat and also in the events Telegram channel. So we will move on to our next team of speakers. So now that we're generating all this good randomness, how can we use it? Our next two speakers will cover use cases for DRAND. Alejandro Hevia is a professor of computer science at the University of Chile, a founding member of the League of Entropy. Alejandro works on applied cryptography, cybersecurity, and public policies related to privacy and computer security. Vaughan is founder and CEO at Ethereum, a blockchain proof engine using the blockchain as a platform to verify data, files, and business processes. Ethereum is the most recent addition to the League of Entropy. We'll learn about the use of randomness in government processes from Alejandro, and then hear Wayne discuss why Ethereum switched to DRAND for their chainpoint proofs. Let's welcome them to the stage.
Cool. All right, let me ensure this. Can you see my slides? Yes, can you hear me well?
Yes.
Yes.
Perfect. All right. So first of all, thank you for the invitation to talk here. My name is Alejandro Hevia. I'm a professor at University of Chile. I'm the head of the Randomness Chile project, which is a randomness beacon that we have here in Chile. There are a lot of people behind this project, so I would like just to thank Camilo Gomez, who is the lead developer, but there's many people doing the fantastic job here, so it's just not me. So I was asked to talk about some applications. I would like to talk some applications of public randomness that we have developed in Chile. So even though they use our beacon, the idea is that they could use something like the League of Entropy, actually randomness generated by DRAND or something like that. So just a quick head up here about what we are. We are essentially, we started working in 2017 to try to create somehow an extension of try to replicate and extend the randomness beacon by NIST, but with a particular goal was to provide transparency and trust to digital services that rely on randomness, okay? Our idea was to use this in a way to provide transparency to some processes. And this is something I would like to talk here. I think Luke mentioned it before, but just a point is that our beacon, although it uses a similar approach as the one by NIST, we have a different way to generate randomness in the sense that we sample different sources. Particularly, one of them is the source from earthquakes. So that's why the seismic girl is standing on top of the earth moving. So we like that pretty much. And so let me just go into the point right away. Since the motivation was to provide transparency, we decided to look into places where transparency was an issue, in particular with randomness. And in Chile, we do have, as in most countries, we have an agency which is in charge of auditing the expenditures of taxes, you know, how government spend taxes, whether they actually do it following all the regulations and in proper ways. Here in Chile, it's called Contraloría General, which for people in the US, it would be something like the Comptroller General. This is the independent agency in charge of preventing essentially politicians to mismanaging the funds. And what they do is they actually do a random selections of people, of government officials for audits. And the main problem they had for a long time was that, of course, they don't have enough funding to do audits in every single government official. So they had to pick people at random. And because of they couldn't, the process was not really that transparent, they were frequently accused of political persecution. So for them, when we approach them to tell them, look, you can do this in a verifiable way, they were really excited because that will be a way to provide more transparency to the whole process. So you guys have an idea how this works. The main idea, this is one case, but the main idea in this particular case is that you have a process in which you have a universe, a list of all possible government officials who could actually be subject to audit. And the idea was to select some of them at random. Of course, in practice, it was a little more complicated, but the overall idea was that we managed to create a way in which we could take some of these inputs and make them public, make this input in public here. And somehow the whole selection process was being done outside of this agency using the output of a particular pulse from the beacon, or particularly it could actually be a particular day. For what exactly happened here is that the Contraloría actually commits to perform this selection, say on January 1st to noon, and on that day it just provides all the inputs in a website, and the selection is being done with the pulse, with the randomness from the pulse of that particular date and time, and the output actually is also public. And the whole process is designed in a way that you can recompute it, okay? Again, any external observer can recompute it. So that's quite an interesting aspect to do the verification. Of course, there are many details. The selection needs to be done in a way with is based on a particular number, which is called the risk factor. And the risk factor, there's several buckets of risk factor. So there is a little more complicated selection, but it can all be done and actually could be recomputed by any external observers, provided that they know exactly when this took place, so they are able to recover whatever randomness was generated in that moment and recompute. There are more details, and the more detail is that this is the most basic aspect of the selection. There's some other selection that requires to use data which might be sensitive. So you might have some private inputs. Let's say sometimes the risk factor associated to a particular government official is based on another data. Let's say how much money they make, whether they have properties or not, and that information might be sensitive to reveal. You cannot reveal it. So we have a second solution in which you use commitment and using some range proofs to prove that people belong to a particular bucket of risk. So you can actually select it with a certain distribution there. So we did that. Unfortunately, this is a project that's been on hold at this moment because, of course, like everyone in the world, we are going through this pandemic, and this is, we hope to resume this project soon. But actually, one of the key issues here is that the process to provide transparency is even though it might be simple initially, providing transparency when you have private input requires some testing, because you need to convince people what we are doing is correct. And we believe that according to our initial prototypes that we're actually doing it. And there is another so can you hear me?
Yep.
Yes.
Okay. Somehow of course, computer got frozen somehow. Hold on, just give me 1 second. Here we are. Right. Sorry. I apologize. Right, and there's a second application that we have is that to be able to, with the electoral service in Chile, you probably don't know, but in Chile, the poll workers are not government officials, so they have to be selected by, they are selected at random among all the citizens who are able to vote. And of course, that for a long time, there was a source of controversy because people were complaining that they were selecting again and again, and the process was not really fair. So we used the public randomness to actually provide a more transparent process there. And in a more interesting application is that in a project, in an initiative that is being done with the Chilean Congress, we created a particular scenario in which this is called deliberative convention. Is an idea from political science, actually from Professor James Fishkin from Stanford, to invite random citizens to get together and to talk about a policy, some policy options about, medical care, some policy related to the country. And the idea is to bring a subset of all citizens to discuss about this issue, and hopefully, since it's a random selection, the output of this discussion is more representative for the country. And we actually, this is something that has been done in other countries, in the US, in Europe. This is for the first time, will be done here in Chile, and our participation is to provide the random selection of the citizens, which is actually a way to everyone to get convinced that this is a fair process, and every people in the country has the same chance to participate. There are some smaller projects that we are working on. Just to mention a few. As mentioned before, to be able to audit elections, risk-limited audits. We have some interesting project with private randomness to try to provide verification of a certain process without really revealing the randomness being used in a way that's more specialized. And of course, some of the other projects you have discussed here before about using a consensus algorithm and so on. So I'm pretty happy to answer some questions later, but our goal here, just to mention, there's uses here of randomness, which are very, in my opinion, very important for the transparency of certain processes, especially those which involve decisions that affect a large collection of people. I will believe there is plenty to do there. So thank you. I think on this, I will have to yield to Wayne, I think.
Thank you. Thank you. Hello, everyone. My name is Wayne Vaughan. I'm the CEO of Ethereum. We work on a project called Chainpoint, which allows you to create a timestamp proof that anchors to the Bitcoin blockchain. And back in 2017, when we were launching a new version of the technology, Alejandro, is there a way that you can turn off your screen sharing?
Yes. Sorry, that's okay. No sorry, Wayne. I thought you will take it over. Thanks.
No, I'm just going to be talking old school style. We're going to do an analog here.
Perfect. Okay.
Using words. So when we were launching a new version of the protocol back in 2017, we wanted to find a way to be able to prove not just the existence and integrity of data, but also provide some strong evidence of when the proof itself was created. And so just to kind of give a quick overview of the way Chainpoint works, you take a hash of some data, you send it out to a gateway on the network, you get back a V1 UUID, and at some point in time in the future, after a bunch of magic happens in the background, you'll be able to get back a timestamp proof that has a commitment to, or is anchored to the a block on the Bitcoin blockchain. And so what we, and just for some context, the way that people use this is for things like document timestamping, being able to prove that data that's collected during clinical trials hasn't been manipulated, those types of use cases. So, so what we wanted to do was not just prove the existence and integrity of data, but we also wanted to be able to prove when a proof was created in a certain time window. So what we did is we started injecting the NIST randomness beacon into our into every Chainpoint proof. And what that allows you to do is essentially you're able to verify that it provides, proof is maybe too strong of a word. It provides pretty strong evidence that your proof was created after that randomness, the pulse from the NIST randomness beacon was generated, because you could never know the value in advance. So we ran this system for about, I'd say about 2 years, and thousands of nodes on the network, lots of organizations using the technology. But we did notice some things, some problems with using the NIST randomness beacon. Number one is that sometimes it went down. There were intermittent outages. It didn't really impact the core ability that we were delivering to users of the network. But it did bother us. And then secondly, we noticed that the NIST randomness beacon, the software development on it seemed to slow down. And at one point in time, NIST published a document that said, hey, if you're going to make a randomness beacon, here's some of the properties that this randomness beacon should have. So that became a signal for us to look for something else. And after lots of evaluation of different options, we settled on using Drand and became a member of the League of Entropy. And there's a couple of advantages from switching from the NIST randomness beacon to using Drand. So number one, it's permissionless. We didn't have to ask anybody for permission. We simply evaluated the technology, downloaded the software, started running our own Drand node. And as of July 9th, 2020, every chain point proof from our systems is concluding a Drand pulse instead of a NIST randomness beacon pulse. So it's permissionless, and then also the NIST Drand, the Drand beacon issues a pulse every 30 seconds, whereas the NIST issues a pulse once per minute. So although time precision and accuracy is not important for our use case, it is an added benefit that we're getting basically double the time precision for the from Drand. So essentially, we were able to join the network. We get double the time precision. It was a no-brainer for us. So we set up a NIST Drand node, and we're planning on running 3 in the future. And it was very, very easy for us, and didn't really take any time at all. So if you want to learn more about Chainpoint, you can go to github.com/chainpoint and learn about what's there. And I want to thank everybody for asking me to come and talk a little bit today about what we're doing.
Thank you very much to Alejandro and Wayne for focusing our attention on real-world implementations of randomness beacons. The idea of random citizens discussing an issue to find a representative decision is really interesting. It sounds like an even more representative version of sortition. And I really enjoyed the fireside chat style explanation of Chainpoint and why Tyrion chose Drand. Please remember, if you're watching along, to post your questions for Alejandro and Wayne in the Zoom chat and in the event's Telegram channel, and they'll get to them during the Q&A. So I think we're ready to move on to our next speaker. There we are. Excellent. Our next speaker, Nicolas Gailly, is a research scientist in the crypto lab at Protocol Labs Research and the creator of Drand. His talk will start from the cryptography that Drand uses, and then gradually move on to highlight the different Drand protocols. Let's welcome Nicolas to the stage.
Hello, everyone. Hi. So yeah, I'm gonna make a deep dive into Drand's cryptography for about 20 minutes. Let's see how far I can get to. And so hopefully you get a better understanding of how this network is working by the end of this talk. So first, just one quick slide about why the implementing Drand was, let's say, a good idea at the time, and I think it's still a pretty good idea at this time. Is like there was different solutions, distributed solution that we knew at the time. So I started Drand in 2018. Were good in theory, but in practice quite hard to achieve. So when you have tree-based communication, it's very hard to maintain availability. If this node is down, how do you communicate message to the other one? When things are based on leader election, how do you make sure you replace a leader if one is down and things like this? It's far from trivial, both in theory and implementation, even harder. Now we have VDF, which is starting to take a much bigger weight in the space. So it's a very promising approach, but so far it's not production ready, I would say. It realized it's quite recent. There's many constructions which are very recent. So in cryptography, we prefer to have some time to make sure they are correct. It relies on different assumptions. So it requires a cryptonymic analysis because we need custom chip, custom hardware. It's far from easy as well. So we had this different technology that we use threshold cryptography that's now starting to get, let's say, around 20 years old anymore. So it's starting to be at least good enough for trying to use it in a production ready manner. So this is why I started Drand. I will be quick on this slide because you know what League of Entropy and Drand is now by now. So let's just say that yeah, it's been around for a while now. I started this on the side around 2018, and we launched the first experimental network last year in June, and now we just launched the League of Entropy production network last month. So let's go over really quick on Drand. There are basically three phases. There's a setup phase between all the nodes, between the first set of nodes, let's say. You can think of it as a trusted setup party, where we run a multi-party competition between all these set of initial nodes. Then we have the ongoing current randomness generation. So we just combine information in a very easy way. I'm gonna show you later to just create this randomness. And then we have some resharing phase where we pass from one group to the other, where we can change the group members, the group size, the threshold associated with the group, etc. So we're going to go into all of these three phases. So I'm just going to go a little bit, trying to bring back some details about Hamiel secret sharing, even for Bryan and the first phase already introduced a little bit over it. Hamiel secret sharing is very simple to understand. So it's basically mathematics of high school. So if you get a polynomial here, so you get a first coefficient, then all coefficient times x, up to a degree t minus 1. Okay, so you say this is your polynomial. And s here is the first coefficient, which is your secrets. And so basically, you're going to want to evaluate this polynomial to different points. So f of 1, f of 2, s of n. Okay, and this will be your shares. Okay, so you got a share 1, share 2, share n. When you want, what you can do with this is then after you can aggregate all those shares. So any set of t shares here will be able to aggregate it. You will be able to interpolate the polynomial f of x via Lagrange interpolation to retrieve this s of x, and then you will be able to retrieve this secret here. So basically, any set of t shares here will be able to recreate this polynomial here, so you can get back the secret. That's the basic of the threshold cryptography that Drand use. Here it's Lagrange interpolation. There are over interpolation that we're using, but Drand use Lagrange interpolation. So now we bring this idea further ahead, one step higher. So instead of in this slide, we have one dealer which creates a secret here, and then he will create the polynomial, and then he creates the shares here. So the dealer knows the secret here. What we want to do is actually to have nobody that knows the secret. So we want everybody to be a dealer. So they will create, so imagine there are n parties. Each one will create their polynomial, so f of 1, f of 2, f of n. And they will all put this random secret here. So, and then we'll create the polynomial. So f of 1 will have the s1 secret here, and then we'll just create the polynomial. And there, as before, we will create the shares. So they will evaluate their polynomial at position 1, their polynomial at position 2, etc., up to position n. And what we're going to do here is that at the end of this step, I'm simplifying things, but at the end of this step, we're going to add all the share received for the first node is going to receive all these shares. Okay, and we're going to add them, and this is going to create its final shares. And the final shares is actually representing a share of a secret that nobody knows. It's actually representing a share of the secret S1 plus S2 plus Sn plus up to Sn. So it's a secret that nobody knows. but that such that any subset of T shares, so S1, S2, and up to ST shares, can reconstruct it. So that's basically, we pass from Hamiel secret sharing when we have one dealer that knows one secret and creates a shares, to a distributed key generation where you have n dealers that create n polynomials and where they create a share of an unknown secret. Okay, that's the basic of the distributed key generation. And that's actually what Drand uses here. So we are implementing Drand implements the Peterson DKG protocol. It was originally based from the Daily Skyber library, and then we forked it into the Drand organization now. So this setup is run once at the beginning. So it's a multi-party computation, so it's definitely a little bit more expensive. So it's O(n) squared. We are running on the BLS12 381 pairing curve currently, which is compatible with like many major blockchains, like say the next version of major blockchains. So for example, Zcash and Ethereum 2 and Filecoin are using the same curve. So it can be interpretable in many, for example, smart contract, or even in the basic consensus protocol, such as in Filecoin. So we are running this protocol at the beginning of when we want to launch a new Drand chain. Then how do we generate randomness? So here I get to introduce another cryptographic primitive that Drand uses. We're using what we call pairing-based cryptography. So in pairing-based cryptography, we have a special mapping between three groups, and which is able to solve a hard problem in cryptography when you don't use pairing-based cryptography, which is called decisional diffie-Hellman. And basically, what you can do is, if you have one point here, which is A times R, if you have another point here, it's B times R2. If you apply this pairing operation E, then you can say that it's equal to R1, R2, so the operation of the pairing of R1 and R2 to the power of AB. So this allows you to do this allows you to create, this is a basic to create BLS signatures, which has been around since 20 years now, invented by Bonneau. And the scheme is actually very simple when you look at it. So it's basically, you have a message M here, you take the hash of it, and then you put it over, you exponentiate it with your secret key, okay? This is the signature, so very simple. And the verification, you take the signatures, you take the second base point of the second group. So remember, in pairing-based cryptography, we have three groups, sorry, G1, G2, and GT. So we take this, and then you also do another pairing operation, which is just the hash of the message. And here it's a public key. So P is a public key of your corresponding to your private key. So you just do two pairing operation, or one, depending on the implementation. So the pairing operation is a bit more slower than the regular Schnorr-like signatures. But given the simplicity and the deterministic natures, we have other advantages for using BLS signatures. So as you can say, I've said the uniqueness. So this BLS signature is unique. So because for one given message, you only have one given message and one private key, one public key, private key pair, you only have one signature possible. There's no external randomness coming here. So this gives us a strong unbiasable, not unbiasable, but unique signatures at this point. And then we move to once we have BLS signature, we move to the threshold version of BLS signature, when instead of putting the private key here, you just put a private share. Okay, so the share that we derived here in the distributed key generation, S1, S2, Sn, you will use it to sign here. And then since this operation is linear, you can just combine. You can just combine all these private partial signatures into one full signature using Lagrange interpolation. And the magic works here because this operation is still linear. So then how to verify these final signatures? Just with the distributed public key. You have one, it's like a regular BLS signature in the end. So how does it work? The generation is pretty simple. At each period, so Drand generates a new random value periodically, each 30 seconds for right now on the current network. And the first stage is that everyone, each 30 seconds, everybody will generate new partial signatures and we will broadcast to everybody. And then as soon as a node got a subset of any T partial signatures, which are valid, it will be able to reconstruct the final signatures, and this will be the randomness. So the signature, the BLS signature itself is not the randomness; it's the hash of the signature, because the BLS signatures is by itself a point on a curve. So you don't want to keep the algebraic property here. You want to hash it so it's uniform on the bits. So it's bitwise uniform. So we get unpredictability and unbiasability from BLS properties. We get publicly verifiable. So we are sure that at least T nodes participated and that the value was correctly generated. It's decentralized. It's available under the threat model, which is like at least more than half of the nodes are honest. And it's quite fast because each round is a bunch of signature to aggregate. So it's so far it's quite fast. So the chain is actually, we increase, Drand makes as a randomness chain. So where we sign the previous randomness that was being created. So I will go over quickly because it's very simple. Basically, every 30 seconds, we sign the previous randomness that was generated at the previous round and the round number here. So round, previous randomness. It's very, very simple. I want to go a little bit quickly because I'm running out of time. So here I'm going to talk about a nice feature of Drand is how to make the network evolve. So because we have one network at the beginning, one set of nodes at the beginning that run this DKG and may generate randomness, but what if we want to change the network size, what if we want to change the network members, then we have what we call resharing mechanism. And the goal is for us to be able to change the threshold and the number of nodes, but we also want to keep the same distributed public key. So from the client point of view, there is no change at all. It doesn't need to change anything. So as long as the clients get the initial public key, then it can verify randomness regardless of the evolution of the network behind. And that's a key feature of Drand that allows to not care about what happens behind the scene, which is much simpler this way, because key evolution and key updates are still another thing which we deal very well in computer science. So in this case, we are able to make new shares for the same key. And that's one of the key features here. So how does it work? So if you understood how the DKG worked before for the secret here, we were putting a random element. So each node was using a random element, like I'm going to talk in the next slide. It could be Lavalump, it could be coming from Drand or whatever. But here we're going to put if for now we want to reshare from an old set of nodes which already have shares to a new set of nodes, which might be completely disjoint, by the way. It can be new, completely different nodes. Can be the same as well. So what we're going to do is we're going to take our share and we're going to put it as a secret of our polynomial here instead of putting a random element. So we're going to do exactly the same as the DKG in the first DKG. So we're going to create our shares here, but instead of adding them as we did with DKG, we're going to interpolate them here. That's the key difference here. So we're going to interpolate all the shares here, and it's going to create a new S'1 share here, and all these S' shares are linked to the same private key and the same distributed private key and distributed public key that were generated during the first DKG, except that now it's new shares, so they are refreshed, and the old shares are not valid anymore. Because, I mean, assuming the threat model, there's more than half of the network that is honest, they're not going to accept this new share because they moved on to this new set of polynomials here, which won't verify against the previous share. So we did two things here. We created new shares. So we refreshed the shares, and we were able to pass from an old set of nodes to a new set of nodes. And that's really important. That's actually what we did already. I don't know, 2 or 3 times already, or even 4 times in the mainnet League of Entropy right now, to onboard new members and to grow the network. Because as long as you grow, then the security grows as well, because it's becoming harder and harder to correct enough node to be able to get enough shares. So that's what we are using to periodically refresh shares and to grow the network size. And just one last slide, how do we get Drand Lavalumps into Drand? How do we get any kind of random generator from the random utility into Drand? then it's quite easy. Instead of in the first DKG, so it's only for the first DKG, instead of putting a random element here, well, you take your element from the 11, for example, and you put it here. So you transform your entropy from the element here into the 32 bytes element here, and then you run your DKG here. So basically, you can think of Drand as a randomness aggregator. You can use any external entropy system, and then you can aggregate them during the initial stage to create this randomness chain. And so it's not I don't see Drand as a competitor to other entropy system. I see more like as an aggregator of them, so you can use all the benefits of each system. And that's it for me. Thank you. And if you want to participate or happy to hack into Drand, you're all welcome.
Thanks to Nicolas for walking us through the core design principles of the Drand randomness beacon. It's like a glue that holds entropy together. Remember to add your questions and comments in the Zoom chat and in the Telegram group, and we'll get to them later in the Q&A. I think now we're ready to move on to introduce the next couple of speakers. Will Scott is a research engineer at Protocol Labs working on IPFS, a peer-to-peer hypermedia protocol designed to make the web faster, safer, and more open. His research interests center on networking, security, and privacy. Alan Shaw is a core developer of the IPFS protocol and a self-described eternal optimist. Their talk will lay out the infrastructure the Drand team has built to add availability attacks into its threat model. Let's hear about channeling chaos.
Excellent. Thank you, Karola. I'm going to let Alan get the slides up on the screen. Awesome. Cool. So what you just heard from Nicolas is sort of the protocol and the cryptography that's backing Drand. And we've got a really nice construction there that gives us a lot of good properties. And then we've got a bunch of really interesting use cases and consumers of Drand. And there's a host of systems challenges in between, which is that it's not simply the unbiasability that we need, although that is clearly necessary, but we also need to make sure that the randomness that's getting generated by this group of nodes is able to reliably get to downstream consumers that want to make use of it. So there's a systems and networking challenge there in between that we had to think about designing and solving to feel comfortable that a Drand network as it's deployed is something that other production systems are going to feel comfortable using. So this is trying to give a sense of that journey. Next slide. And so really what that problem boils down to in a lot of ways is how do you do this with an adversarial network? And so what I want to do over the next 10 minutes, 20 minutes is we're going to try and define more specifically the sorts of attacks that we want to include in our threat model and try and get that threat model a bit more concrete. And then I'll turn it over to Alan to talk about the mitigations in the systems design that we put in to allow distributions of Drand to stand up to those threats. Next slide. And to start though, I think there is a bit of sort of systems design things that we need to go into. Next. So, and skip ahead maybe too, because what I want to talk about first here is the systems piece of how do we go from nodes having it to consumers getting new items of randomness, right? There's sort of two major classes of threats that we need to think about from an adversarial network. One is an off-path adversary, and so this is someone who is not a DRAND node who is not the consumer and who is not an ISP or a network in between them directly, but is some third party who just sort of doesn't want randomness to work. So if you happen to just be somewhere totally random on the internet, how are you going to try and make DRAND fail? And the other case is that you are on path, and our primary worry is not so much a malicious node, because the relative, we can fall back to the cryptographic protocol to solve that problem, right? Which is if some node is malicious, we'll have the clients just go to other nodes as well. And if clients are going to multiple nodes, then we can fall back on our assumption from the cryptographic level that a majority of nodes are going to be honest and working correctly. And so by looking at that consensus, we should be able to mitigate bad nodes. And so the real problem that we have to solve is what happens if the direct ISP of a consumer or of some set of users doesn't like DRAND. Okay. Next slide. So we are helped in this separation by the DRAND protocol itself. And one more slide here. The random values that we have are immutable. So once a randomness beacon is published for a specific round, it's not going to ever change. And so that makes it easy to cache and means that we can hopefully minimize some potentials for DDoS. The beacons will continue even under some network partition scenarios. So even if there are disconnections of the group members themselves, as long as you've got a threshold in some place, they can keep generating randomness. And as long as any individual group member gets enough shares to generate the next beacon, there can be ways to distribute that. So we have some resilience already at the protocol level that we can take advantage of resilience to partitioning. The random values as signatures of this public key that's been pre-distributed means that each value is self-validating, that a client can by itself in a non-interactive way validate that that value is the value that it expects for a given time period and knows when that value is supposed to happen. The resharing mechanism that we just talked about, that Nicolas just talked about, allows the group to transition without changing the underlying key. And so that means that there's no online key validation or revocation process. So there isn't an equivalent of OCSP stapling or any of these other complexities of needing to have either an online interactive validation process or knowing to check that your security has to be updated. And finally, these things are small. Okay, so we've got a bunch of really almost sort of the best case scenario in terms of the randomness values that we're trying to distribute. And so the sort of high level view of the design that we're going to use to try and get DRAND randomness out to people who want to consume it, next slide, looks sort of like 3 layers. We've got the nodes themselves at the top here. So here you can see a node representing Protocol Labs and another representing Cloudflare. And these nodes are only going to talk to the other group members. And we're going to put in place as much protection to those nodes as we can to prevent any other potentially malicious actor from directly talking to the group members, to the DRAND nodes themselves. And what that means in practice is this dashed line is really sort of a firewall in a sense, that we will try and have all of our DRAND operators implement IP whitelisting to only allow inbound traffic and connections from other approved operators and not from arbitrary external traffic. And that aims to limit the potential for denial of service style attacks against the nodes themselves, as well as making it so that some unapproved member can't start sending messages as if they want to join a group or do any of these other protocol level things and reduce the attack surface. But in creating just a sort of an IP whitelist box, we've protected the nodes to some extent, but we've also made it much harder for anyone to go and directly get randomness. So how do we then make sure that the randomness is widely distributed? So in addition to the nodes, there's a separate binary process that gets distributed either as a binary or as a Docker image, or however it is consumed. The operators sort of do these deployments to some extent on their own, so that there's a diversity of those as well. But these are stateless relays that will be allowed in the operator's deployment to talk to the DRAND node and fetch new random values. And these relays can be used with a CDN infrastructure to provide horizontal scaling and allow increasing amounts of client requests for randomness without having those requests directly translate into more requests on the DRAND node itself. And the main goal here is, how do you think about denial of service style attacks and protect against those? Cool. So this is sort of our 3 levels. And with that in mind, we can now sort of look a little bit more deeply into the attacks themselves. Next slide. So since we've got a relay and a CDN around it, the specifics of how those two things work are going to be somewhat operator dependent, right? If I am to deploy a DRAND node on Cloudflare's infrastructure, the specifics of how their load balancing and CDN caching work is different from if it's on the AWS cloud or if it's in my own physical deployment. But in broad strokes, the attacks that we want to make sure that we can be resilient against, next slide, break down into about 3 things. So the nodes we should allow to not have overwhelming of requests, and that's what our IP whitelisting is trying to do. We don't want unknown nodes to attempt to join. And we want to be able to protect against impersonation. So DNS getting changed and other members thinking that a DRAND member is somewhere else or is someone that it's not. The relays themselves, we're worried about an intermediary network performing DNS hijacking attacks or blocking those IPs or blocking the specific service that is advertising itself as DRAND. And we also need to figure out a way to protect it from being overwhelmed with requests. On the client side, we need to be able to protect against false responses being returned. So if there is a man in the middle or a malicious network that misdirects a client, the client may get bad results back that have been impersonated and needs to be able to protect itself against those. And we want to limit ourselves from targeted network disruption. So if the network is injecting resets or dropping packets when it knows that something's DRAND, we want to be as resilient as we can to those style of attacks. So having laid out this sort of broad set of malicious network activities, I'm going to turn it over to Alan to talk about the mitigations that we've put in place to try and gain confidence in our DRAND distribution at being able to handle these.
Okay, cool. Hopefully you should still see the slides and not also my notes, because they will get in the way. Okay, I'm going to tell you about some of the mitigations we've taken to avoid network attacks. And they have the intent of boosting availability and uptime and should allow DRAND to continuously provide verifiable, unpredictable, and unbiasable randomness forevermore. Hooray! So there are a few simple mitigations that we've made to protect members of a DRAND group. Will has already covered them a little bit. But firstly, public traffic never actually directly hits a DRAND node. So to compromise a DRAND node, you need to go through a CDN or a relay or get in by some other means. But it means that DRAND nodes can be completely segregated and isolated from the outside world. And the only inbound access that is needed needs to come from other nodes in the group. And so for this, as we already mentioned, an IP allow list is in effect, and that just restricts traffic to just the IP addresses of the nodes in the group. And so finally, public API exposure is optional, so members can contribute to generating randomness without actually having to distribute it. And that just means there are fewer vectors available to attackers. Okay, so the second mitigation, failing fast with bad requests. This is about mitigating against overloading a node. And so we can define a bad request as a request that's invalid or uncacheable, or valid and just lots of them, like a denial of service attack. So valid requests for current or historic randomness round or the chain info are cached indefinitely. And since all requests are cacheable, only like very few requests actually make it to the DRAND node itself, and no external traffic actually talks directly to the DRAND node, except for the other nodes in the group, as I mentioned before. So in the diagram here, we can see a path of a bad request to a DRAND node. And so a naive kind of DDoS attack can be mitigated by the CDN provider. So if we're asking for a particular historic round lots and lots of times. A request for like a far future round, so a round that hasn't yet been generated, can be discarded at the HTTP relay level. And then finally, requests that try to talk directly to DRAND nodes over like gRPC are discarded by the IP allow list. So we can get closer, but we aim to drop bad requests as soon as possible. Protocol Labs run a network observatory, and the idea is to measure how effective the distribution of randomness is, so its latency and its availability from multiple geodiverse sites across the globe. So this is quality of service for the distribution network. And it provides insights like some distribution mechanisms are faster in some regions. And it also provides like a baseline for what we expect the latencies to be. And so we can set up alerting to tell us when they're observed to be different and we know that something's up. We also closely monitor our portion of the DRAND network, and by monitoring randomness generation events, we're in effect actually monitoring the entire League of Entropy DRAND group. And so we graph our measurements for our info team, but we also run a publicly accessible status page, and that could be accessed via the DRAND website at drand.love. GossipSub is an alternative distribution mechanism, and that helps with network scaling because it's peer-to-peer communications and distribution over different transports. libp2b can use TCP, QUIC, WebSockets, other transports to distribute the randomness. So let me first explain a little bit about libp2p and GossipSub. libp2p is a modular network stack for building peer-to-peer applications, and GossipSub is a PubSub implementation. So it allows applications to subscribe to topics, and other applications publish messages to the topic, and the message is pushed to all the subscribers for that topic. And that's all done peer-to-peer and completely decentralized. So how does this work in DRAND? Well, Protocol runs a DRAND GossipSub relay, and it publishes randomness to a particular topic. This topic is comprised of a DRAND identifier, a protocol version, and a chain hash, and that allows other groups, so not the League of Entropy, to potentially have their own chain and distribute it over GossipSub as well. And DRAND GossipSub clients subscribe to that topic for the chain they want randomness from, and GossipSub delivers randomness from any peer on the network. And so that makes it particularly important to verify the beacons that are generated, because there are many mans in the middle. So in this diagram, notice that the peers do not have to be connected directly to the main relay. So the network can scale without introducing additional pressure on the first level relay. And so GossipSub can also provide some resiliency to DNS attacks and HTTP traffic censorship. And it's been found to be the fastest delivery for new randomness in some regions, as I said before. One experimental mitigation we have is the Twitter relay. Hooray! So it's another distribution mechanism that it could potentially mitigate against downtime or HTTP relays or block DNS to DRAND API endpoints. It is mad science. Do not use this, but let me tell you how it works. It tweets round number and signature every 30-second period. Due to Twitter character limitations, any client that were to consume this randomness would need to derive the previous signature and generate the hashed randomness value from the signature. But that's okay, that's not too difficult. It's currently not useful because the account exceeds the maximum 24-hour tweet limit by only around 200 tweets. So it means that every 3 hours we miss a few beacons, so that's not good. Maybe someone knows someone at Twitter who can help with this. There is an experimental JS client that's available. I will post the link somewhere later, but that's the Twitter relay. Okay. If your application relies on getting randomness as a critical component of its operation, then you're going to need a smart client that takes advantage of this DRAND infrastructure we've been talking about. So we built 2 DRAND client libraries, one in Go and one in JS, and they have multiple transport implementations for you to use. So for example, you can create multiple HTTP clients for different DRAND HTTP API endpoints. And you can also create a gossip sub DRAND client. And there's also a gRPC client, which is what the HTTP relays use to talk directly to the DRAND nodes. But anyway, multiple transports allow the client to mitigate against adverse network conditions like blockages or unavailability. And so basically, if the trains aren't running, you can take the bus. So these concrete implementations can be passed to a base DRAND client, and that allows you to consider them all as just one single client. And the base client adds speed testing and failover functionality. And the clients that it has are speed tested periodically, and the fastest client is always used. Watch channels or live feeds of randomness as it's generated, the fire hose of randomness, as it were, they are automatically and transparently switched out. So we're always watching the fastest client. And that means we receive randomness as quickly as possible in the event of changing network conditions. If a client fails to retrieve randomness, then we use a different one. And the clients are ranked in speed order. So if the fastest one fails, then we move on to the second fastest one and then the third fastest one. And any failure sends a client to the back of the list. But it's okay because it can recover because we've got the speed test, and it will be speed tested again, and then it can become the fastest if it recovers. So that's awesome. The other really important thing that it adds is chain and beacon verification. And that means that the client verifies the chain that we're receiving randomness from is the chain we expect to be receiving randomness from. And we also verified the signature of every beacon that is delivered against the public key of the chain. And we can optionally verify the whole chain or a subset of the chain from a known trusted previous beacon. So it really makes sense to use a client library if you care about the security and integrity of the randomness values you're consuming. Finally, the base client also adds caching. So asking for the same beacon multiple times doesn't result in multiple requests to the API. It's also worth noting that it does aggregation of watches, which essentially means that multiple requests for a live feed will only result in one underlying request to the API. So that's good. There is an option for auto watching, which is for priming that cache, so that if you need some randomness later that has been generated, then it's already there for you. You don't have to go and get it. So that's also super useful. Okay, so the final mitigation, we made a bunch of important changes to the way the project operates and the systems we used. A security audit was completed by Sigma Prime. We set up continuous delivery to a monitored DevNet, and we set up automated regression testing. We have a PR approval process, so every pull request has to be built and tested and have a approving review. An automated linter runs on every pull request. We have a documented procedure for reporting security vulnerabilities. We have a documented release process, and that includes mandatory signed release commits. Our test coverage has been surfaced and is continuously tracked. And then finally, we run multiple test nets. We have a test net for the League of Entropy right now, and there's also one running at the moment for Filecoin, and that basically enables a dry run of onboarding and offboarding new members to the DRAND group. And in the case of Filecoin, it allows for like a real world testing of disaster recovery in the event of halted randomness. So that is all of the mitigations, and that is how you channel chaos. Thank you very much for listening.
Thanks to Al and Will for explicitly and emphatically laying out the importance of network security and threat modeling to randomness protocol robusticity. Drop your questions about channeling chaos in the Zoom chat and in the Telegram channel. And we'll get to them in the Q&A, which is coming up next. So we're moving into the block 2 question and answer session. Thanks to all of the speakers from our second block of talks, Luke, Nathan, Alejandro, Wayne, Nicolas, Alan, and Will, for setting the stage for a great Q&A about Drand and the League of Entropy. You can still participate in the question and answer session via the chat streams in the Zoom webinar and the Telegram channel. Your points might spark someone else's great question or lead to further great ideas. Now, on to the questions. I think I will be kicking this off with a question from the chat. This question is directed at Luke. In addition to providing Drand as a public service, do you have or expect to have an internal need for public randomness?
So at least at this time, we don't that I'm aware of. There were some use cases for using this randomness for deciding which employees at the company would be able to go to New York when our company IPO'd, basically. So there are some sort of use cases like that, but currently none that I'm aware of company-wide. Mostly we want to provide this as a service.
Thank you. The next question, also from the chat, is directed at Wayne. Yes, there we go. If Drand is provided as a public service, why did Tyrion choose to run your own node?
Because we wanted to be part of the infrastructure. We want to be part of the community of people who are supporting this. We're Chainpoint is an open source initiative, and we just think that it's important for us to be able to be part of the infrastructure. And that was one of our complaints, or the shortcomings of the NIST randomness beacon, is that there was downtime for a service that we had a reliability on a third-party provider, but by running something ourselves, we could provide at least some guarantee that our machines could talk to the machines that we were running.
Thank you.
I think it's important to note that Tyrion is actually running a node in the League of Entropy mainnet currently. That's, so you are participating in the public randomness service, but that is available now. I think this was maybe a misunderstanding with the question.
Thank you for that clarification. We have the next question, also from the chat, is for Alejandro. What was your experience getting non-technical individuals, like politicians or government officials, to understand the pretty technical considerations around bad randomness and the advantages of using a public beacon?
Well, in my experience, the only thing I can say is that you have to take it slow. You have to start with the basics, start with a very simple explanation that usually what it means is that let's, first of all, trust us, trust the University of Chile, trust this organization. And then once they start doing that, they realize, wait, how do we know you are not lying? And then you move to the next step and say, okay, perhaps you don't have to trust a single entity. You want to trust a collective. Okay, that's good. So it takes a while for people to go from something that they really don't see a problem with the randomness, just they need randomness, to the point in which they realize different type of the qualities of randomness. So in my experience, that you have to just take it slow, do prototypes little by little, step by step. Don't try to move too fast all the way down, because especially politicians don't see it takes a while. So a lot of patience. Sorry, we would love to move faster, but sometimes you have to move slow enough for people to realize potential attacks. They realize potential problem for them. People might be, they are fully aware when people accuse them of essentially putting the thumb on the scale. Okay, they know that, and they want to, but they don't know exactly how to move that to elsewhere, to a different entity. So you have to just take it slow, and I can do this for you, and then perhaps a lot of people can do this for you. Perhaps there is infrastructure. Look, this is designed in a way nobody controls it. You can rely on that. Many people are relying on that. So that's my experience.
Thank you very much for that answer. The next question will be asked live by Jeff. Jeff, are you with us?
Yes, I'm here.
Go ahead.
So I'm Jeff Coleman from Alpha Ventures. My question is for Nicolas. Usually the primary design separation between sort of the classic distributed protocols and the more blockchain style crypto-economic protocols is whether or not you include more fine-grained economic incentives and rewards and punishments, things like that. Is this a design element that Drand plans to include in the future, or is avoiding those types of design elements a specific objective?
Yeah, so historically, I've been, let's say, I started to implement Drand after we had a collaboration with Dfinity, which is using kind of the same technique to provide randomness on their chain, but it's effectively implementing the whole blockchain with all the crypto economics parts. And the thing is, there are so many blockchain and other systems that needed randomness, but no one was really, most of them were just assuming we use a secure source of randomness, but there was no system at the time that could provide it. And so I started to code Drand with a specific design in mind, that it should only provide randomness, and it should it should only do this, like do it very well in the Unix philosophy. So it's a specific design objective to not do anything else and to not have any crypto economics design part. So you can think of it like as DNS servers, as NTP servers, as Tor relay servers. It's not run on the crypto economic part at all, and it works. I mean, it works pretty well. So that's the basic goal, to become as a foundational internet service, not necessarily tied to any blockchain, not necessarily tied to all this complexity layer above here. Does that answer the question?
Yes, thank you.
Okay, our next question comes from Doug Hill, and it's directed at Alan and Will. Doug asks, are you using an OAuth token to uniquely identify the participants?
So for group members, the group members each have a TLS-based certificate of the DNS name corresponding to their organization that is used for a mutual TLS authentication between the different group members, and that's used for after the IP-based whitelisting, how the Drand group itself is communicating. There's not an OAuth level access.
Thank you. Clear answer. The next question we have is from Vas in the chat. It's directed at Luke. And Vas asks, wouldn't some of the random processes correlate in the League of Entropy, given an exogenous event? If there is an earthquake, then seismic in Chile and the lava lamps in Cloudflare would exhibit a correlation, perhaps?
So the good thing about entropy is the more diverse entropy sources that you collect, you don't lose entropy through this. So I guess the short answer is no, we're not worried about that, because little blips in one or two entropy sources wouldn't affect the randomness or the overall entropy of the final result. But yeah, so even just separate machines getting randomness from dev-urandom, unless there was a bug in the implementation, then we wouldn't be concerned about the correlation like that.
Thank you. The next question, also from the chat, is for Alejandro. And the question is, what are the next real or physical world applications for randomness beacons beyond what you've mentioned already in your talk?
Well, there is a couple of them which we haven't mentioned. Is that there's one class of application that has to do with transparency, but for scientific experiments. There's an old controversy about people faking the experiments and so on. And we are talking with a certain groups of scientists to be able to commit to a particular experiment and in a way that they can do the sampling in a fair way. So let's say the chair of a journal can know exactly the whole thing. It has more transparency. The whatever is reported on the results. And also something more interesting perhaps is the whole idea of using private randomness, this idea of moving away, a little bit away from public randomness to private randomness. And there's all sort of challenges there. And there are many different open problems. And I think it's something we will need, and we are looking for different ways to provide it in a way that, let's say, small devices can get it and people can get it. And more importantly, from our perspective, is that the whole process of you getting the right private randomness could be verified. So it means like it could be yield a verifiable process. So there are some other alternatives other than the one that I mentioned before.
Thank you for that extra information about the future of randomness. I think the next question we have is for Wayne. It's from the chat. The question is DRAND randomness already being used in your production service? Do you have some numbers for how many proofs have used DRAND so far?
Yes, as of July 9th, 2020, every chain point proof has a DRAND pulse value instead of a NIST randomness beacon value inside of it. I can't give you any numbers about the number of proofs that are actually generated because the way that chain point works is that there is a certain, there's an aggregation infrastructure in place where hashes come in and they're used to construct a Merkle tree. And the root of that Merkle tree is the only information that is sent up to the certain nodes that are in the network. So that root value of that Merkle tree could represent one hash that's been sent to those nodes, or it could represent millions that have been sent to those nodes. So, of course, there's a large number of organizations and developers using Chainpoint. So it's some, reasonably large number, but I couldn't give you a number.
Thank you. The next question is for Nicolas. And the question is, for a certain number of nodes n, what is the value t chosen in DRAND? Does the security model assume that nodes could act maliciously? By signing the round in previous random, doesn't the protocol allow any t nodes to pre-compute all the future randoms ahead of time and impact the unpredictability?
Okay, so I'm going to answer one by one. So the first one was about what's the threshold value using DRAND. So the minimum threshold value we have to put to respect the cryptographic assumption we are using is at least more than 50%, and this is what we are choosing. So we are choosing like you divide by 2 plus 1 basically. So just strictly more than 50% number of nodes is a threshold. So that provides us best availability mechanism, let's say, robustness. So does the security model assume the node could act maliciously? Yes, of course. So during the DKG, we support the same number of malicious nodes, so up to the threshold. So after the DKG, when we started the first initial setup phase and to the end, after the end, there might be some nodes which are excluded during this because they behave maliciously or their network was down for some reason. So it's not the same group before the start to the end of the DKG. And on the first question, you touch a very interesting point of DRAND. So what the question with threshold, any threshold system is what happened when you assumptions are broken. So basically, what happens if a malicious attacker controls more than the threshold of nodes? And this is true for many threshold systems, basically. So in the end, what the attacker can do is actually he can predict the chain. So we lose the unpredictability mechanism. However, we do not lose the bias. We don't lose the unbiasable property. That means even if the attacker knows for some time the chain, he cannot bias it in any way, because the chain is already kind of since we don't inject entropy into it, the chain is already kind of fixed in the mix. So there's no. So we definitely lose the predictability, but we still are still able to keep the bias, the unbiasable property.
Thank you. I think we have time for 2 more questions, and then we'll move on to session 3. The next question is going to be asked live by Marcel Yakish. It's for Alan and Will. Marcel, are you with us? Well, I think we lost Marcel. I will ask a question in between while Marcel gets ready. And then, okay, the next question then from the chat is again for Nicolas. And the question is, what is the benefit of the catch-up mode in DRAND? And what if someone can compromise the wall clocks that DRAND depends on?
So I guess it's an insider question because I didn't talk about catch-up. It's a nice question. So the catch-up mode in DRAND is when the network was down for some time. So basically there was more than the threshold of honest nodes which were not alive and could not send the randomness out or aggregate enough randomness. And so in DRAND we keep a consistent time to run mapping. But when the network doesn't produce any randomness, there's no randomness produced anymore. So when the network is back up, so all the necessary connection, the minimum number of necessary connection is online again, is effective again. Then nodes will generate randomness faster than they should to be able to catch up at the right time, at the right round corresponding to the current time. So the benefit of the catch-up is to still be able to provide this time to run guarantee. So in most of the time, you can associate a timestamp to any DRAND round. When DRAND was down, there's going to be a few rounds which are going to be created later than what the timestamp should be, not before. That's a guaranteed assumption, but maybe later. And then as soon as they caught up, the chain has caught up to the current timestamp, then this guarantee started to be back online. So this allows for applications to be able to determine exactly which one they want to use at which point in time. For example, in Filecoin, we have a one-to-one mapping between which Filecoin round which DRAND round will be associated to which Filecoin blocks. And this is a very nice solution and very easy to understand. Very easy to process about, to reason about for analyzing the whole security of the consensus protocol.
Thanks again. I think I'm going to go ahead and ask Marcel's question, and that is to Alan and Will. What happens if more than n/2 nodes become Byzantine? Is there a cryptographic or cryptoeconomic mechanism to make sure the generated value is truly random?
Do you want to take that, Alan, or I'm happy to if you want?
Okay, for it.
So I think this is somewhat similar to the question that Nicolas just answered. If you break your threshold assumption, so over the threshold number of nodes are acting maliciously, they still cannot provide biased or incorrect random values, right? So they are able to reconstruct future random values on the chain. And so that unpredictability thing is something that they now have access to. But if they distribute a Byzantine value, so something that is not actually the signature, then clients that get that value, when they attempt to verify it against the public key that they're hopefully distributed with, or that has come in at sort of the beginning, will know that that is not a valid signature from the group key. And to be clear, they can sign anything, right? Because they control the full threshold. But what they can't, each element in the chain is the signature of a sort of known value that is deterministic. So they can't sign some arbitrary message and have that message be the expected message for that round. The message that you expect for each round is the round number and the previous randomness. And so if they try and make a message that they sign that's anything else, the client knows that that's not the expected derivation from the previous round, and that the chain is not progressing in the way that it's expecting. And you can verify that by itself, even in that failure case.
Thank you very much. And with that answer, I think we'll close out this session of Q&A. Thank you to all of the participants in the chat and the Telegram channel for some really great questions. And thank you again to our panel for some really great answers following some really great talks. And okay, now we're going to move on to the third and final block of talks, all about the future of randomness. So welcome to the third session of the Randomness Summit, where we look to the future of the field. Our first speaker is Joseph Bonneau, professor at NYU's Courant Institute of Computer Science, who works on security-related topics in applied cryptography, security economics, and human factors. Joseph was the first person to formulate the concept of the VDF. His talk will provide a brief introduction to verifiable delay functions, including basic definitions, desirable properties of VDFs, and some historical perspective. Let's welcome Joseph to the stage.
Okay, hopefully everybody can hear me. Let me share my screen. Okay, could I get a thumbs up that you can see my screen? Great. All right, so glad to be here. It's really exciting to see so many talks about randomness and lotteries, which is something I've been working on in my academic career for the last 4 or 5 years now. So you've heard about VDFs a lot today. I'm going to try and give a little bit more of a technical introduction to exactly what they are for people who haven't seen them before. Also outline some of the different parameters of the design space, hopefully set up the 2 talks coming after me, which will talk more about the latest developments in actually implementing VDFs. But I did promise a little bit of historical perspective. I'll tell you about a really old way of doing public randomness, doing lotteries, which is a pretty good deep dive on the internet to do if you haven't before. Which was a form of gambling that was called different things in different places, but usually the numbers game or the policy game. This is a headline from the New York Times from 1935 about some organized crime members being busted for running this game, for running the numbers. It actually dates back, at least in America, to the late 1800s. But the game was really simple. Here's actually an example of somebody who took out a ticket. You can see it became fairly well organized issuing these tickets. What you see here is sets of 3 numbers. So you could pick any 3 numbers you wanted. It was a proto lottery. And then you would write down the amount you wanted to bet. So low-level gang members would walk around and give out these yellow tickets. You would give them some money, as much as you wanted to lay on these different sets of numbers. And then the next day they would come back and pay you if your numbers actually came up. And the source that they actually used in New York, they used different things in different places. Sometimes they used sports or specifically horse racing things, but in New York, they just used the total number of shares traded on the New York Stock Exchange for the day before, which was published in the newspaper. So they just truncated the last 3 digits, and that was what people wagered on. So this general idea of using stock markets as a source of randomness has been, it's very, very old, way pre-blockchain. So let's dive into that a little bit, because this is something that people still propose doing in in modern times. And it's something I've thought about a fair bit. So obviously the modern formulation, you wouldn't just truncate the last 3 digits. Bryan talked in his talk about how it's it's better to hash everything. It makes it more difficult to manipulate, although you still can by brute force. So let's take a very, very simple example where our randomness beacon is just going to be the hash of the closing price of 3 stocks on the New York Stock Exchange or some large stock exchange from the day before. So the way that you'd go about manipulating this, if you were an attacker, you'd wait until right before the value is going to be finalized. So you would try to get that last mover advantage. It's been described already in a lot of different scenarios. Same thing for the stock market. And then you would look at different possible small perturbations of the near final value and say, what would happen if I executed 1 extra trade, if I pushed the price of this stock up or down by a penny? You'd have a fairly large, exponentially large as you had more stocks included, space of possibilities that you could explore. And you could simulate what the lottery outcome would be for all of those different perturbations. And then, if you have the capability, you can try and force whatever the best one is for you to happen by executing or not executing those trades. So if you're a high frequency trader, this type of attack is actually fairly low cost and easy to do it. It's not easy to become a high frequency trader with extremely low latency, but once you achieve that position, you could somewhat reliably manipulate the source of randomness. So notice the key step is that you have to be able to simulate different lottery outcomes for different potential courses of action that you could take. And of course, what I didn't say is that for this attack to work, you have to simulate that very quickly. Right, so I did mention you have to be a high frequency trader. You have to be able to decide very quickly whether or not to act. So the general idea, which I think is quite powerful that can fix this and other weak sources of randomness, is to add a delay. So to add a function to the process, which can't be computed quickly. And that way, an attacker who's trying to do an attack like this, when they attempt to simulate what the lottery outcome will be for different possible courses of action that they can take, they don't actually get an answer. Their simulation doesn't complete until it's too late to actually execute any trades. Right, so obviously if that delay took even on the order of minutes, by the time you had the results of any of these simulations, the market would have closed and you've lost the opportunity to act. So this applies to a couple different sources. Like I said, the 2 historical ones that were used by organized crime throughout America were asset prices, also sports scores, and the modern one, which of course wasn't available to Al Capone, was blockchain data, which is we're all presuming is a better source. Although I would like to say at this point actually that I do think it's worth thinking about financial data as well. But I claim that for all of these sources, using a delay function helps by making it impossible to tell what the results of any course of action that you might take are until it's too late. Just to show you, same paradigm plays out in the blockchain space. If you have multiple competing blocks that are found in the same slot, a miner might have some ability to manipulate. The simplest thing is they can just choose which of 2 colliding blocks they mine on top of. You could think about a more devious attacker who tries to actually bribe other miners in the network to favor one chain or another. But again, the key component is that you see these different blocks which have the potential to become canonical, and you can simulate what the lottery outcome will be if any of those blocks does become canonical quickly, so that you can choose which one is good. So again, if you add a delay so that you can't simulate that very quickly, you'll lose the opportunity to act by the time you know which of these blocks you actually want. Okay, so how do we actually build this delay function? At this point, the talk's going to be a little bit more technical. I promise not too technical. So a VDF is a cryptographic scheme. There's 3 functions. There's some sort of setup function. And in the setup, you specify a time parameter, which is how long you want, how much of a delay you want. And lambda is just a standard cryptographic security parameter. And then given those public parameters, there's an evaluation function that takes an input X, maps it to an output Y, optionally gives you a proof of correctness. And then you have some verification algorithm, which just verifies an input-output pair. And again, maybe it takes that proof. And the three properties, it's very, very simple. If you remember the acronym VDF, there's basically three properties that this thing needs to have, stated informally here. It needs to be verifiable. There needs to be an efficient verification algorithm. So informally, we want verified to be much faster than evaluation. There needs to be a delay. So this thing needs to be inherently sequential, and it should take t steps to solve. And it has to be a function. So it has to have a unique output. For any input X, there has to be only one Y that it maps to. If there were multiple possibilities, then we would lose consensus about what the lottery outcome would be, and it wouldn't be usable in the randomness setting. Okay, so again, you just have to remember the three letters VDF, and it basically describes exactly what it is. So it sounds simple. Turns out we didn't really know how to actually build such a function until the last few years, where we've seen a lot of exciting research to that end. And it's kind of interesting because if you take away any of the V, the D, or the F property, there was kind of a known construction at the point that we started this research that are, well, the first two at least are pretty trivial. If you don't care about efficient verification, I think Vitalik mentioned this, you can basically just iterate any one-way function in a long chain and you get a delay function. If you don't care about delay, if you don't care about the problem being inherently sequential, there's all sorts of verifiable functions that are easy to verify, hard to compute, but easy to verify the answer. Discrete log is an example. The other one, if you want a verifiable delay that doesn't necessarily have a unique answer, there is something called a proof of sequential work, which is a cool building block from crypto theory. As far as I know, I'm not sure it's been used in practice, but it is out there and you can look it up if you're interested. So anyway, all of these were known at the point in time when we formulated VDFs and wanted to build one for the first time, but it took a little bit of creativity to figure out how to get all three properties at once. And you might have also heard of time lock crypto, time lock encryption, or commitment schemes. Those have been around since the 1990s. You may have seen them in the news recently because a very old one was broken for the first time. So that's also a related notion that's much older, and sometimes people get confused what's the difference between time lock encryption and VDFs. It turns out the structure is actually very, very similar. The main difference is just with time lock encryption, somebody knows the answer Y before X is published. So it doesn't really work in this public verifiability setting. It sort of requires a trusted person to set up each specific puzzle. But otherwise, the computation is actually very, very similar. Okay, so I'm going to not describe the two main constructions because I'm hoping the next two talks will. But I'll just give you, just so you have a flavor of how this is even possible to have a function that's much faster to verify than evaluate. The simplest example is just computing a square root mod p. So this is this idea has actually been around since the early 90s. You can take a random integer mod p. Computing its square root takes order p steps, but then verifying that square root is correct takes exactly one step. Notice here, I should say I've been quite informal about what a step is. That actually depends on your application. A step is some basic operation, which might be a group operation, it might be an exponentiation, or in this case, a squaring. Of course, that squaring itself, is maybe you don't think it's an atomic step. It can be broken down further than that, but that's at the level that we're looking here. Okay, so like I said, I should say that this technically isn't a VDF. The gap between evaluation and verification isn't actually big enough by our definition, but it's kind of an almost VDF. But modern designs that actually do achieve the stronger definition, there's sort of basically two families. There's ones that are based on repeated squaring, So there will be a talk coming up about that. You can work in different groups. And then there are approaches that, as Vitalik outlined earlier, you take a long chain of operations. It might actually be that square root mod p or cube root mod p, and then you apply a generic proving system to prove that you did it correctly. So I believe these are the next two talks are going to drill into the details of these. But I'll just show you some generic things that you'd want from a VDF. So if you could sort of build the Platonic ideal of a VDF, you'd want it to have a very efficient setup or even no setup at all, and you'd want that setup to be untrusted. In practice, sometimes the setup is a slightly more expensive polynomial algorithm, and some VDFs, particularly squaring in an RSA group, do require a trusted setup, although there's been a lot of work on how to do that in a multi-party way or other approaches to deal with that issue. You also want efficient evaluation. So ideally, it has to take t steps by the definition. Ideally, it's 2 steps on a single-threaded processor. But we do allow in the definition, maybe you need a limited amount of parallelism to actually finish computing in t steps. That's fine. But it shouldn't be some massively parallel operation. And you need efficient verification, of course. That's the V property. So ideally, it's just some small polynomial of lambda, which is going to be, the size of it has to be at least order lambda. But we allow that, maybe it's some small polynomial, but notice, at most it's logarithmic in t, right? So it takes t steps to compute, can't take t steps to evaluate. That would just be, evaluation. Sorry, it can't take t steps to verify. That would be verification by re-execution. So the definition, which is sort of arbitrary, but I suppose we wrote the first paper, so we got to choose the limit. We said we'll call it a VDF if it takes up to log t steps to verify. More than that, you're not saving enough, and we don't think it's efficiently verifiable anymore. But again, ideally, the verification is constant no matter how long the computation takes, and the good constructions that we have available, they actually do achieve the ideal here. So they do achieve, constant verification in T. Okay, and then probably the most important property is this difficulty for an adversary to accelerate this computation. So we model an adversary, as is typical in cryptography, we try to give the adversary a lot of power, a reasonable amount of power, but not an exponential amount of power. So the adversary is allowed a large, not exponential, but polynomial pre-processing step. So you could think they try to build a table of known results or known partial results that will speed up their computation later. And then they also get a lot of parallelism. So they get a polynomial number of processors. Again, neither of these steps can be exponential, or it becomes sort of trivial. You can just pre-compute everything, or you can solve it by brute force. But we give them that much power. And then we say that the adversary can't compute it any faster than sigma t steps, so some function of t. And ideally, it's just t. Ideally, they can't knock any steps off the process at all. But for certain VDFs, there might be some very small tweak where if you throw a lot of parallel processors, you get a very small speed up. It depends on your exact construction. But again, the ideal is that there's no algorithmic way to speed this up at all. Note, this is the very important part. I said there's no algorithmic way to speed it up. Of course, this has already come up in Vitalik's talk, but an adversary can always try to speed up the individual steps, right? So if you think about the gap between when the input X is published, the attacker might have some supercomputer. So they might finish, they're doing the same number of steps. They might be doing the exact same computation. They don't have some algorithmic speed up here, but they might still finish first just because their computer is much faster, right? Of course, we want to give the honest party the latest and greatest, not a Commodore 64, but there's, you might assume there's always going to be some gap. And this gap is typically called A max now, which is sort of the best speed up that, the best attacker we can imagine would have over the honest party that we know exists, sort of the hardware that we know we've built, and we're running operationally. And again, exactly what this value is going to be is very important depending on your application. Ideally, it would be 1, of course. It might be a factor of 10 or 100. Reasoning about this is, I think, one of the most interesting open challenges in this space. The good news, kind of the whole theory behind this, is that it's actually very hard to speed up a processor. You may have noticed that Intel stopped putting the clock speed of processors on their TV ads because they haven't changed it about 10 years. And there's kind of this old saying, adapted from networking, that it's very hard to improve latency. You have to bribe God to go faster at a certain point. And another way, another data point I can show you to try to convince you of that, the world record, at least that I was able to find, for the fastest CPU, I think that's for a CPU that's actually running x86 for an overclock processor, is something like 8 gigahertz, which is not very good when you consider that a standard iPhone you'd buy from the Apple store is over 2 gigahertz. So we're not really able to achieve a speed up of more than a factor 3-ish over the standard hardware that everybody carries around in their pocket. Okay, so last couple things to mention. Some other things that distinguish different VDFs from each other. Quantum resistance. Some VDF schemes are quantum resistant, some aren't. I think in practice, maybe what we care about the most, like I said, we really care about this A max parameter. So the simpler it is to implement the evaluation circuit, the easier it probably is to reason about how much it can be sped up. And of course, as was also mentioned earlier, these are some new cryptographic assumptions, some of which are more new than others. Of course, you get a lot more good feelings in crypto the longer the assumptions have been around and have been tested. Okay, I'll just say to conclude that we've been talking a lot about beacons and randomness, but there are some other VDF applications out there. In particular, like a very simple one, computational timestamping, just showing that a piece of data has to be a certain age because you've computed a VDF on top of it. And this has been proposed as a way to prevent front running, which is kind of cool. You can sort of prove I didn't just come up with this this transaction to broadcast to the network after seeing somebody else's, because here's a VDF computation that took 10 minutes. So obviously, I thought about it at least 10 minutes ago. Okay, so that's what I wanted to say. I'll look forward to seeing the next 2 talks, and I guess we'll reconvene for questions after that.
Great. Many thanks to Joseph for putting VDFs in historical perspective as we explore the future trajectories for this technology. I was not expecting to hear about numbers runners, but I loved it. Please remember to put your questions in the Zoom chat and in the Telegram channel, and we'll get to them at the Q&A. So our next speaker, Kelly Olson, comes to us from Supranational, a product and service company developing hardware-accelerated cryptography for verifiable and confidential computing. This talk will discuss the importance of hardware acceleration for evaluating RSA VDFs and generating their associated proofs. It will also discuss the latest performance results across a variety of hardware platforms. Let's welcome Kelly to the conference.
Excellent. Thank you very much. Let me go ahead and share my slides here. Okay, hopefully you can see that. Yeah, so thanks everyone for having me today. As mentioned, I'm going to be talking about hardware acceleration of a specific VDF construction, and that is the RSA VDF construction. And what I'll talk about today is I want to just give a sort of a background on sort of how this work was completed and what the results of the work is. But also I want to provide a number of links for folks if they want further information to go in and read more about this work and ideally to join in and participate in the work that's going on around this hardware acceleration topic. So just to begin and give folks a little bit of background, while I'm presenting this talk, ultimately this work is the culmination of a large number of participants in the VDF Alliance. And folks may not be familiar with the VDF Alliance, but it's a collection of academic, nonprofit, and corporate collaborators that are building open source software to improve the security, scalability, and privacy of blockchain protocols. And really the goal of the Alliance is to use hardware acceleration to make these emerging cryptography techniques more practical. And I'd really urge anyone that is really interested in this topic and would like to learn more to visit both vdfresearch.org, which is a fantastic resource maintained by Justin Drake, who will be presenting next, and also vdfalliance.org. And just to give some folks some context for some of the activities that happen within the VDF Alliance, we generally have weekly calls where we talk about the progress and the state of the art in VDFs. This undertaking to actually bring VDFs into production is sort of a multifaceted research project that involves, expertise in cryptography, in theoretical lower bounds research, in multi-party computation. And so if you have interest in any of these areas and actually looking at how we could bring VDFs into production, really urge folks to take a look at the various websites that I mentioned, and please, reach out and let us know if you'd like to contribute in this. We do generally have a VDF day once or twice a year. We most recently held one at Stanford during the Stanford Blockchain Conference. And if this is something you're interested in attending in the future, there is a sign up on the vdfalliance.org website where you can get more information and be notified about these things. So just to provide, a last bit of context, Joe did a great job talking about sort of the three main functions of a VDF. In terms of hardware acceleration, the two things that we're really going to be looking at is both the eval function, which in the case of RSA VDFs is iterated modular squaring, and the proof function, which is where you generate a cryptographic proof that can be efficiently verified. And this activity is ultimately about making modular multiplication as quick as possible. So, one question to ask is why hardware acceleration? So as Joe had mentioned previously, there are limitations and sort of theoretical results about how much the overall VDF can be sped up. But as he alluded to, there are ways to speed up the individual iterations, and that's really what this talk is going to be focused on. And what I'd like to sort of give some context for is why this is actually an important activity. So just to start, at a very high level, really the goal of these VDFs is to take some sort of pseudo randomness, whether that be stock prices, whether it be blockchain data or sports scores, and create this strong randomness that is unpredictable. And in order to do this, what we have to do is we have to make sure that even someone with an extremely fast, maybe they have maybe they're running at 10 gigahertz or 20 gigahertz or something like that, ensure that they can't reach that output before they have to choose and make a contribution to the pseudo randomness. And so the very simplistic way that I like to think about it is essentially in the VDF protocol, people have to choose a direction that they want to drive a car. They're going to do some number of iterations by driving to that car. And then when they get to a certain distance, they're going to find an output. And that output is ultimately the strong randomness. And so the main goal is to make sure that even if someone is very, very fast with, has very fast hardware, that they can't drive that full distance and get the output before they have to contribute this pseudo randomness. So in a very simple example that we have right here, we have your average user, and maybe he's running on a normal laptop or a desktop. And we can think about him as computing this VDF at something like 10 miles per hour. We may also have an attacker who wants to be able to bias this randomness, and he may be much faster. And this ratio between the average user and the attacker is something that we call Amax. And ultimately, the goal of all of this hardware acceleration research is to minimize this Amax number. So in this very simplistic case, if an attacker has, say, 2 hours to contribute to the pseudo randomness, and he's moving at 50 miles an hour, we need to make sure that he has to travel at least 100 miles so that he can't know what the output is at the end of the road, sort of when he picks his direction that he wants to travel. And in this case, that delta or that Amax is 50 divided by 10 or 5. So why do we want to minimize this Amax? Well, when you take these VDFs and you move them into production, AMAX dictates how, a variety of parameters for your randomness, such as how many concurrent VDFs you need to run or how often you get randomness output. So for instance, if the attacker is 5 times faster, your average user is going to have to run 5 VDFs concurrently to get the same number of outputs as the attacker, or they're only going to be able to produce an output once every 5 of these contribution periods. So all of this effort that's gone around reducing, sort of the time to evaluate this for the average user helps in a variety of ways. One, we get faster time to randomness. So we don't have to run the VDFs as long before we get randomness output on the chain. The second is that we can get more frequent randomness for the same number of chips. The third is that we have to run less of these VDFs in parallel, which reduces the overall sort of operational costs of running these systems. And then last but not least, one of the main benefits of VDFs as a sort of proof of work is that they require a lot less energy consumption. And if we can reduce the number of these VDFs that have to be run in parallel, then we reduce that energy consumption even further. So the first thing I'll talk about is the VDF evaluation. As Joe mentioned, really we sort of know from a theoretical standpoint that this modular squaring operation can't be sped up any more than just doing the iterated operation itself. But as he mentioned, there are actually ways to speed up a single iteration. And the two things that we look at here is the first one is algorithms. And these are not algorithms that speed up the VDF, but these are hardware and multiplication type algorithms that enable you to do these squarings faster than other algorithms. And then the second one is how fast does the VDF run? So every hardware has a set of resources to do these modular squaring operations. And by using custom hardware like FPGAs and ASICs, you are able to do a single iteration of the VDF faster. So to provide just some context for sort of how quickly this hardware acceleration has been progressing, Joe and his team at the Applied Cryptography Group at Stanford, I believe they first introduced the concept of VDFs in around June of 2018. By around March of 2019, the VDF Alliance had both developed a novel algorithm for doing fast modular squaring and also implemented this on an FPGA. Again, as Joe also mentioned, this was used to solve a 20-year cryptographic puzzle that ended up, while it wasn't the first person to solve the puzzle, it was on the order of about 20 times faster than the person that solved the puzzle first. And then since then, since solving that puzzle, we went and did a $100,000 open source hardware competition where we ultimately got another 2x performance improvement for the VDF. And we've now completed an ASIC design of the VDF as well. So, without going deeply into the details of exactly how this is possible, the sort of net takeaway on the evaluator is that we've been able to increase the speed of computing a single 24-bit modular square from about 1,000 nanoseconds per squaring on a CPU to around about 5 nanoseconds on an ASIC. And what this means in practice is that we've actually, if the average user has one of these ASICs or the average participant in the VDF protocol has one of these ASICs, we basically have to run 200 times less of these ASICs in parallel. We can get 200 times as much randomness delivered on chain, and the energy consumption is ideally also about 200 times less. So, it's been a really interesting thing to look at something like VDFs that were, thought to be not able to be, sped up greatly, and actually realize that, through the use of custom algorithms and custom silicon, we're able to actually speed them up by about, over a couple orders of magnitude. To give you an idea and some context for exactly why this happens is when you do a VDF on a traditional CPU, like an iPhone or an Intel laptop or something, there's a set amount of hardware that you're in a fixed sort of hardware configuration that you're working with. So most architectures today are 64-bit architectures, and they have 64-bit multipliers. And what this means is that if you want to do a 2048-bit squaring, then you actually have to do, you have to use these multiplication units, dozens of times. And what we're able to do through both FPGA and ASIC type architectures is that we're able to actually do these 2048-bit squaring all in a single operation. So we can actually make the multiplier, 2, 4, maybe even 10 times bigger than what's actually possible on a CPU. So I'm not going to go, very deep into the details here, but we do have an open source implementation of a VDF evaluator today. It's a fully parameterized design, so this design can be used to support other cryptographic curves and curves of different sizes. Today, the way that the curve or the implementation is done is that it uses a collection of 512 bit multipliers that sort of all operate in parallel, and then we have sort of a large reduction tree that then gets you to your final modular reduction. But what I would advise is that if folks do want to learn really more about these specifics here, we have a whole design series on medium.com/supranational that will walk through this design. And if you're interested in learning more about how hardware can accelerate not just these VDF functions, but sort of other cryptographic functions, I would invite you to watch the hardware acceleration talk delivered by Simon Peffers at day 2 of the 2020 Stanford Blockchain Conference. So, kind of the net of the state of the art for VDF evaluation is that we have an implementation today that runs on an FPGA, and it's about 20 times faster than what happens on a CPU. It runs in about 70 nanoseconds per iterated square. And we have line of sight to implementing this on custom silicon and bringing that down roughly, another 10-fold. So the next thing that I'm just going to talk about briefly is sort of the state of the art in VDF proving. So again, evaluation is just one part of this AMAX calculation. And what we want to do is generate fast VDF proofs as well. And the results that I'll show use an algorithm that was originally developed by Benjamin Wesolowski, who was, I guess, the first person to actually create an instantiation of a verifiable delay function. This algorithm was then enhanced by Argonne Design and was further improved by the VDF Alliance. The key thing here about the VDF proving is that it's very amenable to parallelization. And so what we've been able to do is basically remove almost all of the sequential operations out of generating the VDF proof so that you can sort of spread out this computation as much as possible. And we can look at a variety of designs like FPGA, GPUs, and ASICs for this. So just to give you, a quick idea of what that looks like, this is a look at modular multiplication in terms of millions of operations per second on a variety of platforms. And what we see is that we're able to get about a 35x improvement in proof generation time by using a GPU platform. And the reason that this is that GPUs really just have thousands of tiny cores that we can leverage to do this highly parallel work. And one of the interesting things that we find about this work is that these primitives that we're accelerating, modular squaring, modular multiplication, modular exponentiation, they underline a wide variety of cryptographic primitives. And so what we're hoping to do sort of as we move forward is to use these fast GPU implementations to improve things like faster snarks, to provide better strong randomness, to maybe provide anti-spam protection in certain protocols. And so that's sort of one of the things that we're quite excited about is taking these learnings that we have from this hardware acceleration and then applying it to other cryptographic primitives. Great. So I know that's been a sort of whirlwind tour of the state of the art, but just to talk about some of our future plans, I think the first thing to say is that VDF hardware is available today and it's already been used, right? So we were able to crack a 20-year-old time lock puzzle that was supposed to take 35 years, and we did in about a month. We also have an RSA VDF service that's running using block hashes from the Ethereum blockchain. And so sort of as we move forward, we have two main goals. The first is to support projects with this VDF as a service. So if you're a project that needs strong randomness and say is operating on the Ethereum blockchain or another blockchain, one of the things that we can do within the VDF Alliance is actually provide you with this fast VDF hardware. The way that this VDF service works is that it's basically an API-based portal where a user can submit some randomness in. We'll evaluate the VDF on that FPGA instance running in the Amazon cloud. We'll generate a proof using an Amazon GPU instance, and ultimately this will get returned to the user and can be efficiently verified on chain. So that's the first thing that we're looking forward to do. And then the second is that we're looking to move forward and actually prototype an ASIC. So we're hoping that by the end of this year, the ASIC design is sort of fully ready for tape-in, that we could tape in the design in the first half of next year, and that by maybe the second half of next year, we will actually have operating RSA VDF chips that can be used in production systems. So that's kind of the conclusion of the state of the art on hardware acceleration of these RSA VDFs. All of the work that we've done is open source. If you'd like to see the code for this, you can go to github.com/supranational/hardware. And there's a variety of resources on vdfresearch.org and also the Medium blog series if you'd like to learn more about some of the work that was done here. All right, thanks everyone.
Thank you very much, Kelly, for a great talk about the intersection between cryptography and computer architecture and hardware. And also thank you for introducing the VDF Alliance. Between the League of Entropy and the VDF Alliance, the Randomness Summit has more superhero leagues than Comic-Con. Remember that you can add your questions for Kelly in the Zoom chat and also in the Telegram channel, and we'll get to them at the Q&A. But first, let's move on to our final speaker of the day. Our last speaker, our cleanup hitter in baseball terms, is Justin Drake, an Ethereum 2.0 researcher at the Ethereum Foundation. Justin has a background in mathematics and a history of entrepreneurship in the blockchain space. His talk will be about snark-based VDFs, the leading candidate for quantum secure VDFs in ETH3. Let's give a warm welcome to Justin.
Hi, everyone. Let me just share my screen. Up. Okay, so today I'm going to be talking about post-quantum VDFs, basically VDFs that can withstand more scalable and powerful versions of these beasts. That's the IBM Q with 50 qubits. And one of the reasons why I'm interested in post-quantum VDFs and more generally in post-quantum cryptographic primitives is that in the context of Ethereum, we want to have a quantum roadmap for all the primitives that we use in Ethereum 2.0. Okay, so my talk will be in 3 parts. Basically, I'll give some context on the VDFs that we have today and why they're not totally satisfactory. And then I'll talk about the VDFs that we want. And then finally, challenges to actually getting to where we want to be. Okay, so first I'm going to talk about the VDFs that we have. So we have a bunch of pre-quantum designs, and most of the VDFs that we have are pre-quantum. So we have VDFs based on RSA groups, VDFs based on class groups, VDF based on Jacobian groups, and all these groups things, they all fall under this one bucket called groups of unknown order. And there's this quantum algorithm called Shor's algorithm, which is very good at finding orders of things. And so all these constructions kind of die in one go in the context of a quantum world. We also have a construction which is based on isogenies and pairings. Isogenies can be quantum secure, and I think that was one of the motivations for exploring isogenies-based VDFs. But unfortunately, there's this pairing component of this construction, which means that it's not, unfortunately, quantum secure. And then we kind of not a VDF, but still part of the wider randomness story is, of course, the threshold BLS cryptography, which is used in Drand, which is used in Definity, and which is also not quantum secure. And to my knowledge, there's no quantum secure upgrade to that today. Okay, so that was for the pre-quantum stuff. What about post-quantum stuff? So we do have a few quasi-VDFs. So we have this notion which we call proto-VDFs. So the VDFs which have all the properties of VDFs, except that the verifier has high parallelism. So in order to verify the VDF output in a fast way, you need to have lots of hardware. And so this is the approach that Solana has taken. And basically, the simplest proto-VDF here is a hash chain. So Solana uses a SHA-256 hash chain. It breaks down the long hash chain, which is the sequential evaluation, into baby chains. For each baby chain, they share a checkpoint. And then they send over the checkpoints to the verifier, who will verify each baby chain in parallel using GPUs, which have lots of parallelism. So that works great, except that the verifier, you do have a verifier which is kind of expensive. And then a very similar idea is sloth, which is basically a slightly more sophisticated version than the hash chain. It's basically a hash chain where the hash chain is hard to compute in one direction and quite a bit simpler to verify in the other direction, but the asymmetry between the evaluation and the verification is only a constant factor, a factor on the order of, let's say, 100. So it's quite a bit of an improvement over hash chains, but in practice, the verifier is still too expensive. And then we have another basically post-quantum attempt at a VDF, which are called weak VDFs. So the notion of a weak VDF was defined in the original paper with VDFs, which defined VDFs as well. And basically, it's the dual to the proto-VDF. Proto-VDFs have verifiers with high parallelism, and weak VDFs is the opposite, is the prover that needs to be big. And so this is kind of problematic from a cost perspective because it's expensive to be big, but it's also not great for decentralization. And this is the approach that Starkware Labs has taken with the Vidu proof of concept, which are actually live on the Ethereum mainnet today. And their approach is to use sloth, which is this permutation polynomial, and a post-quantum snark to basically take the easy verification of sloth and compress that whole thing as a big monolith into a succinct snark. So you can use different post-quantum, you can use your favorite post-quantum snark, I guess. You can use Stark from Starkware, you can use Fractal, you can use Redshift, you can use Spartan. But I guess if you do this one-shot monolithic proof, then when your time parameter grows, your hardware will need to grow as well. And this is not just an academic point; it has real practical consequences. Where you're going to need machines which have hundreds of gigabytes of RAM and have tens of CPUs and things like that. Okay. I think the previous talks kind of went through sloth already. I'll go through it quickly. So basically, there's the evaluation, which is hard, with, for example, taking a cube root in a finite field. If your finite field has n bits, it will take roughly n sequential repeated squarings to take this cube root. But verifying cube root is very easy. You just need to take that number and multiply it by itself 2 times. So you raise it to the power 3. And so you have this asymmetry between evaluation and verification. And sloth is basically, let's just have many of these asymmetric computations, and we glue them together with a little mixing permutation here. And so you see the evaluation in one direction is hard, but the verification in the other direction is several times easier. And what the VDO proof of concept design is that they took the easy side, which is, let's say, about 100 times easier than the hard side, and they tried to take that and compress it in roughly the same amount of time it takes to do the evaluation. So they compress it into a succinct proof, and they do this as a one-shot way using a powerful prover. So think some sort of server or like some sort of large machine on AWS. Okay, so that's the context in terms of where we are today. So I guess where we want to be is we want to be in a position where we have a quantum design, which is not really a quasi-VDF. It's neither a proto-VDF nor a weak VDF. It's like a real strong kind of VDF. And it turns out there's a small variation of VDO, the current VDO design, which is really nice and which achieves what we want. So instead of doing this one-shot proof of a very large statement, we're going to break down the evaluation into chunks. And so here we have 2 chunks, and we have a final proof. The goal is to get this final succinct proof. And instead of having a monolithic proof step, we're going to have many intermediate proof steps. So every evaluation chunk will have a corresponding proof. And this is in the context of what's called incrementally verifiable computation. So when you use it for VDFs, you could say it's an incrementally verifiable VDF, an IVDF. And the idea is that as you go along and you add more evaluation, well, your proof updates. And here, this proof here, for example, is a recursive proof. What does a recursive proof mean? It means that it proves that the evaluation here was done correctly and that the previous proof here verifies, which means that this evaluation was done properly and the previous proof verifies, et cetera, all the way up to the beginning. And in order to have a chance, for the proof system, which is kind of heavy machinery, which has overheads, to catch up, to keep up with the evaluation, we use this slough idea, this permutation polynomial idea, where there's this asymmetry between the hard side and the easy side. So here we have the easy computation that is incrementally proved down to a small proof. And one of the interesting things is that this is actually the original design in the paper by Bonnet and Joe and Ben and the 2 Bens, Benedict, from 2018 that defined the notion of VDF. And so we're kind of going full circle. So we started with this design, which, at the time was impractical, and it probably still is, for a few years impractical. And we've explored the space with RSA, class groups and Jacobians and isogenies and VDO. And eventually we're going to tie back the loop and go back to this design. At least that's my prediction as things stand today. And one of the things that you might want to do when you're doing these recursive proofs in the context of quantum secure snarks is that you want to use these snark-friendly hash functions like Poseidon or Rescue or MIMC. And the reason is that often you'll be verifying these Merkle paths in the verifier circuit, and in order for the recursion to be efficient, you might want to use these snark-friendly hash functions, but you also want to use maybe a traditional hash function like SHA-256 for the very last proof, the terminal proof, so that it can be verified efficiently in CPUs and in contexts like the Ethereum virtual machine, the EVM. Anyway, that's a detail. So one of the properties of this really nice design, this iterative design, is that you have a pipeline prover where the proving closely follows the evaluation, and they move together in lockstep. So you have evaluation, which is broken down into chunks, and then you have corresponding proving chunks. And one of the things that you want for this design to work well in practice is that you want the proving to be at least as fast as the evaluation. So you kind of want a one-to-one correspondence in terms of performance between the proving and the evaluation. And so this poses some constraints on the proof system. You need to be able to do these proofs fast enough. Okay, and what are the kind of the benefits, some of the benefits of this really nice post-quantum design? Well, you have cryptographic benefits and hardware benefits. The two big cryptographic benefits, the first one is that this design is plausibly quantum secure. This is why we came here. And the other big cryptographic benefit is that there's no trusted setup. And trusted setups are really, really hard to do properly. And they cost a lot of effort and time and even money to do properly. So having to remove the trusted setup is a really appreciated thing, in addition to the quantum security. There's also hardware benefits to this new design. One is that unlike VDO, which kind of is unscalable from a prover perspective, here you can have a fixed prover hardware, which can handle arbitrarily large time parameters. So if you want to do the evaluation time, to do more evaluation, you want the delay to be longer, well, you just run the thing for longer and the thing just scales. And another benefit is that, at least relative to the groups of unknown order, which can have quite large bit sizes in the modular arithmetic, sloth can run with much smaller modular arithmetic, on the order of, let's say, 128 bits. And so that means that the hardware, your evaluator hardware that you're going to build is going to be cheaper, easier, it's going to consume less energy. So that's also a nice advantage to this approach. Okay, so we've discussed what VDFs we have today. We've discussed where we kind of want to be, or at least one really nice potential candidate, and kind of what are the challenges to getting to where we want to be. Okay, so one of the challenges, and it's an engineering challenge, is prover efficiency. So if you look at the numbers on VDO today, they suggest that if you want one randomness beacon, then you're going to need a big machine, on the order of hundreds of gigabytes of RAM and tens of CPUs. And as Kelly mentioned in the previous talk, if you have an Amax of, let's say, 100, then you're going to need roughly 100 randomness beacons to run in parallel in order to compensate kind of for the slowdown of each randomness beacon. So if you want randomness at a specific pace, then you're going to need to compensate with parallel randomness beacons. And there, if you have an Amax of 100, which is kind of a conservative number, but not crazy conservative, the numbers really blow up to tens of terabytes of RAM, thousands of CPUs, and it becomes too expensive with the technology that we have today to do it without optimizations. The other aspect of prover efficiency is the overhead of recursion, because these numbers are without recursion, and when you add recursion, there's going to be overhead for doing this incrementally verifiable computation. And at every step, you verifying a quantum secure SNARK is, let's say, roughly thousands of hashes in the verifier circuit, and it also means that your circuit will be much more irregular than with sloth. Sloth is essentially the simplest kind of arithmetization that you can get. It's the simplest computation that you can describe in the context of a SNARK, once you have recursion, then things become more messy, and some of the tricks, performance tricks that you had, you kind of lose. So I guess there's two ways to address this proof of efficiency. One way, which I'm optimistic could happen, is just with all sorts of optimizations at various levels of the stack, of the proof system optimizations, or hardware optimizations, like better usage of CPUs or GPUs or things like that. But there's also, a big tool that we can use, which is basically to build a prover ASIC, and that would probably do the job. And one of the reasons the prover ASIC is exciting is that it would be a common good which is not only applicable to VDFs, but it's more generally applicable to speeding up these quantum secure SNOCs in general. That could be potentially a project for various blockchain foundations or companies to pursue, because it's a very neat and appreciated piece of technology that would benefit the ecosystem. Okay, so that's the first challenge, the proof of efficiency. The other challenge that needs to be considered is the various assumptions that we're making. So this design makes cryptographic assumptions, for example, the Fiat-Shamir heuristic, which is very standard, and then it actually makes another assumption, which I call the recursion heuristic. And basically here, once you have a proof system with unbounded recursion, the soundness proofs don't really apply. And from what I understand, there's a decay of soundness for every level of recursion that you add, and you kind of need to wave your hands a little bit to say that it's secure, and hence the recursion heuristic there. There's also a hardware assumption around how much faster can an attacker be relative to the commodity hardware, basically the AMAX. And I'll talk more about this later, and how this changes a little bit in our context. And we also have various cryptanalytic assumptions. We have these various, we need these various hash functions to be secure. And we also have this sequentiality assumption of sloth, which, as it turns out, can be analyzed using the tools of cryptanalysis, things like Grobner bases and whatnot. So it fits in this category of cryptanalytic assumptions. Okay, so just to talk more about this sequentiality assumption, and it turns out that the Starkware team, as I understand, they haven't published it yet, but from what I understand, they found this GCD attack on sloth. And in order to patch the attack, they had to modify sloth and use kind of this state size 2 as opposed to using a state size 1, and that they believe removes the GCD attack. And I guess another interesting recent development is that if you take a generic model of computation in the context of RSA VDFs, then you can actually have really nice results that, for example, repeated squaring, speeding up repeated squaring is equivalent to factoring, which is kind of the best kind of result that you want in this generic setup. And the authors, these two authors are considering extending their results to things like sloth, which would be amazing. Okay, so now let me talk about the hardware assumption, the speed up assumption. So in the context of RSA, you have these really large circuits, millions, tens of millions of transistors, and it's hard to imagine that so-called exotic hardware or exotic processes could be used to tackle these very large circuits. But once you're dealing with smaller sloth circuits, the modular multiplication on the order of 128 bits, then exotic processes become a bit more of a worry, especially if we're talking 10 years into the future, when we'd be deploying this quantum secure infrastructure. So there's things like gallium arsenide, gallium nitride, and carbon nanotubes, which basically take the semiconductor, silicon and replace it with silicon 2.0, a new semiconductor, and you get transistors with new properties, which could have, much higher speed. And so that's something you need to take into account in your attack model. And there's even more kind of exotic and sophisticated ways of doing computing, like optical computing, quantum computing, and RSFQ that also you need to take into account in your model. Maybe sequential equivalence to Grover's algorithm, for example, in the context of quantum, is I guess a possibility. So this is one of my last few slides, and I'm not sure if I have time left, but one of the other challenges is kind of the proof size and the soundness. So right now, in terms of soundness that's deployed in production today, we have 80 bits of conjectured classical soundness, and so that's deployed today with StarkX and Vidu. It's dealing with real money, and every time you want to upgrade the soundness, the proof size kind of increases, at least in the context of the Stark proof system. And really where we want to be is we want to have 128 bits of provable quantum soundness, which is going to come at roughly the cost of 8 times the proof size of what we have today, which is 80 bits of conjectured classical soundness under this very new conjecture, which was made 2 months ago. And this is kind of the target for Ethereum 3.0. And this is my final slide, which I guess is an open problem for cryptographers. Can you design a VDF, a quantum secure VDF, which is based on lattices? And the reason why I highlight lattices is because the Ethereum Foundation is especially interested in lattices because they can do all sorts of crazy unicorn magic, like homomorphic encryption, witness encryption, functional encryption, program obfuscation. So this is an area we want to invest in, at the Ethereum Foundation, and I'm looking forward to researchers trying to tackle this problem. That's it. Thank you.
Thank you very much, Justin, for an excellent talk, walking us through the VDFs we have, the VDFs we want, and the challenges in between, and for touching on the post-quantum era, which I know is a topic of interest in the audience. I particularly enjoyed the rainbow unicorn motif. Please continue to add your questions for Justin and the other speakers into the Zoom and Telegram chat, because now we're moving into the last session of the day, the Block 3 Q&A. I think we've got all the panelists assembled. So I'd like to formally introduce the last session, the Block 3 Q&A, and to thank all of the speakers from our third block of talks, Joe, Kelly, and Justin, for setting the stage for a great Q&A about VDFs and the future of randomness. You can still participate in the question and answer session via the chat streams, in the Zoom webinar, and the Telegram channel. Your points might spark someone else's great question or lead to further discussion after the conference. Now, on to the questions. And the first question is for Joe. And the call is coming from inside the house. It's coming from Nicolas. And he asks, how far are we to having a strong, secure, and efficient isogeny-based VDF, hence a post-quantum VDF?
I think some of that question maybe was assumed by Justin's talk. But yeah, I think that there was a paper in 2018 about VDFs from isogenies that sort of had hope that they would be quantum resistant. But yeah, it turns out, I think it turns out that original scheme is not going to work out. So, I mean, as far as I know, I'm not sure we're really any closer to having an isogeny-based post-quantum VDF. I think, as Justin said, most of the thought on post-quantum VDFs so far has been ones using, using generic proof techniques, using some sort of post-quantum snark system. But who knows? Something from lattices or elsewhere could come up and give us, another family of post-quantum VDFs.
Maybe I'll follow on. Justin, do you have anything you'd like to add to that, to elaborate a little bit?
Nope, I agree 100% with what Joe said.
Great, yeah, I think you covered a lot of that in your talk. I think I will go next for a question for Kelly, also from the chat. How do you determine the attacker speedup for AMAX? Isn't it always dependent on economic assumptions? Like Justin suggested, and even in the absence of new developments, a sufficiently motivated attacker could always re-implement the VDF on a higher frequency circuit, even if that means going cryogenic GAN, GAS, SIGE.
Yeah, that's a great question. So I think I guess there's two ways to look at the theoretical sort of fastest attacker speed, and certainly economics is one way, and to think about, if an attacker has $50 million or $100 million, what sort of technologies are available to them to implement a fast VDF. The other is more from a theoretical perspective, which I think I would hand off to Justin, because he's been doing quite a bit of this this research with complexity theorists, and so maybe Justin, you can talk a little bit more from the more theoretical standpoint.
Yeah, so one of the things you can do, for example, is look at fundamental physical constants like proof of light, speed of light, or you can look at fundamental information theoretic results about computation. So if you, so one example of the latter is if you assume that for example, a repeated squaring VDF can only be done using repeated squaring, well, you basically reduce the problem to understanding how fast can you do squaring. And it turns out that you can analyze the problem information theoretically and look at the circuit depth of a network of transistors that would implement squaring. And so the circuit depth is basically the minimum number of transistors, of sequential transistors that need to go through. And the result that we have right now is that if you want to do n-bit modular multiplication, you roughly have to pay log n transistors. Actually, there's a constant there, which is like 2 or 3 or 4, I forget exactly. So if you're doing 2,000 bit modular squaring, log of 2000 is 11, and then you're going to have a small factor there, like let's say 2, and so then you're going to have a minimum of 22 transistors in your circuit depth. And then you can look at the physics of transistors. How fast can transistors go? If they can go at, let's say, 10 picoseconds per transistor, and there's no way to switch the transistor any faster than 10 picoseconds, then 22 times 10 picoseconds, which is, I guess, 220 picoseconds, is going to be your theoretical lower bound in terms of how much time it's going to take. It doesn't matter how much cooling you have, or how much overclocking, or how much billing you're doing. You're going to have this hard physical constraint on computation.
Thank you.
I guess I would just add one thing too, which is, well, like you said, a sufficiently motivated attacker, I think funded attacker, it is an economic question. And the good news is, as far as we know, I mean, there's no fundamental physical law for this, but you usually get diminishing returns for more money you spent on hardware. If you want to go, twice as fast, it's a lot more than twice as expensive. So, we can deal with this with safety margins, hopefully. But yeah, I mean, at the end of the day, it is kind of just a best guess.
I mean, one of the things that we've seen in terms of sequential computation is it completely plateau. I mean, not completely, but much more so than, let's say, Moore's law, which talks about the density of transistors per unit area, or things like Nielsen's law, which talks about the exponential growth of bandwidth. But sequential computation has plateaued. So if you take a CPU core, it doesn't really, this one CPU core doesn't really go much faster year on year anymore.
Yeah, although it's possible that it's possible VDFs will spur, new research from hardware people and, maybe push that plateau a little bit. But yeah, it would be surprising if we had like 100 gigahertz CPUs next year.
Yeah, I think the one other thing maybe to say is also, that's the point of, I guess, the AMAX parameter is to be able to account for these things and change for them over time. So as we learn about new hardware techniques, maybe new exotic materials, that's a parameter within the protocol that you can always extend to sort of ensure that you have those safety margins, as Joe mentioned.
Great, it'll be cool to see how this virtuous cycle develops in the future. Let me go on to the next question, which is for Justin, and it is, which VDF implementation do you recommend that we use today?
Right, so it turns out there's various VDFs in production or soon to be in production right now. There's Solana, which has the SHA-256 VDF in production in the blockchain today. There's Chia, which is using the class group VDF in a testnet and will be in production very soon. We have the FPGA-based RSA VDF service, which is being run by the VDF Alliance, also live right now. And we also have Vidu, which is also live on mainnet today. And I guess which VDF to go for, it really depends on what kind of assumptions you want to make, what kind of environments you're running in. Are you doing the verification of the VDF inside the CPU? Are you doing it inside the EVM? Are you doing it inside of a SNARK circuit? All of these things will have a great impact on which VDF you want to choose. So I can't really give an answer. The trade-off space is quite large. I think what will happen is that if one party develops hardware for VDFs and they make the investment of, let's say, $10 million, then that will kind of be a way to standardize by brute force which VDF is the best, because it will clearly be better, at least in the one metric, which is the AMAX, which is one of the very important metrics out there.
Thanks a lot. And I see that Joe is pointing us to the vdfresearch.org.
That was a suggestion. I was saying, as Justin was talking, there's enough services running now that we almost need a VDF implementation listing.
That's a great suggestion.
Okay, so not implemented yet. So future directions.
The one other thing I was going to add to what Justin said about whoever gets hardware first is, there's also there's kind of strength in numbers. Like one implementation will probably be once it's established and it's the most scrutinized, it will have the most confidence, and that will lead more people to look at it. And this sort of happens with crypto in general, that there's safety in using the standard things because we have the most confidence that they've stood up to scrutiny. So hopefully, something will emerge, but there are different use cases. So.
Thank you. I think I'll go on to the next question now, which is for Joe. And it is, you said that it might be worth looking at financial data instead of, or in addition to, blockchain data. Do the benefits of using an external high entropy source outweigh the drawbacks of having to deal with oracles?
Yeah, I think it depends on what your goals are, but from my experience trying to sell the concept of VDFs or of verifiable randomness in general to people who come from a traditional lottery world, it's so much easier to explain the stock market entropy source and why it's unpredictable. And at the end of the day, a goal in all of a lot of these applications, at least, maybe not in like leader election, a consensus protocol, but if we want to switch the the NBA draft lottery to a verifiable lottery, or the World Cup draw or some high profile thing, you want there to be a story to sell the public, and it's easier to explain why stock prices are random than why blocks in the blockchain are random, and there is some value to that. So yeah, I mean, there's also in some sense like it's hard to evaluate. Is the risk of like a 12-hour reorg on the Ethereum main chain higher than the risk of somebody moving every price on the New York Stock Exchange for the day? I don't think it's a simple question to answer. So it's possible the security is better with large cap stocks, but it certainly adds the hurdle of needing oracles if you want the randomness available on chain. But there are off-chain applications, right? There are lotteries in the real world that never really touch the blockchain, and for those, the fact that you need an oracle is sort of implied already. So,
thank you. I look forward to FIFA's reaction to a truly random World Cup draw. The next question, it will be given live by Marcel. Marcel, are you with us? Oh dear. Did I do it again?
Yes,
Okay, well,
can you hear me?
This is great.
Oh yeah, so the night is always almost over, or the day, the conference, and we learned a lot about VRFs and VDFs and distributed randomness. But for someone who's not very familiar with the concepts, you can kind of maybe confuse it or the benefits. So I just wanted to ask you maybe if somebody could wrap up the differences between VRFs and VDFs, and since some protocols like Dfinity or Polkadot are rather relying on VRFs, why would you rather, like for Ethereum, rely on VDFs? Do you think they're more secure? I mean, there's obviously some hurdles regarding the hardware and all that makes it harder for the users. So why do you think they're the better choice?
I mean, happy to take this one if no one else will. I mean, I guess a VDF is a VRF, just with some sort of extra delay component. Like a VRF is a very simple thing, and you can use it to build things like RANDAO. I think what you're really asking is, what is the difference in security between the threshold-based schemes and the VDF-based schemes? It's kind of tempting to want to compare VRF and VDF because they share so many letters, but there's really not much magic to a VRF. It's really, I would compare the threshold cryptography versus the time-based cryptography. And the big advantage of the time-based cryptography is that it has this concept of strong liveness. So it will, and strong unpredictability. So even if almost all participants are malicious, you still have liveness. So you still have random numbers coming in, and you still have unpredictability. So it's kind of a honest minority assumption. You just need one person in the world really to be honest, and the thing will run properly. In contrast, the threshold-based schemes, you want an honest majority, not an honest minority, in order for it to function properly. And so it's more brittle, I guess. And one of the things that we want to do at the Ethereum Foundation is we want to never really sacrifice liveness. And the motto that we have is we want Ethereum 2.0 to be World War III resistant. Mm-hmm. So even if some atomic bombs all around the world explode and 90% of the population is gone and almost all validators are gone, we still want the network to function properly. And that's achievable with VDFs.
Are you sacrificing consistency for that liveness, or no?
No. So it turns out that if you put consistency over liveness, then you're losing liveness. But if you favor liveness over consistency, then you basically give your users the option to basically operate in this non-safe, potentially non-safe mode for a temporary amount of time, and then go back to operating normally, as opposed to forcing all your users across the board to shut down during this period where you have this doubt about consistency. So in Ethereum, we want to give people, smart contract developers, the choice to run even during periods where there's no finality of the blockchain, and then eventually there'll be finality. This is very different to a system like Dfinity, where if the randomness beacon stalls, the whole blockchain stalls for all users. And then during this period of non-finality, users have no option to even attempt to participate because the blockchain has stalled.
Thank you very much for a great wrap-up question, Marcel.
Thank you.
And I think with that, we will close the final Q&A session. Thanks to all the participants for some really thought-provoking questions. It's been a great day with a lot of food for thought, and I think we've covered a lot of ground on these exciting topics. And I'd also like to thank the last panel for handling the questions really well and for some exciting talks. And
Thanks.
now into the close. The Randomness Summit is drawing to a close, and I'd like to thank all of the organizers, speakers, and participants for a great meeting. But there ain't no party like a DRAND party, because a DRAND party don't stop. That's part of the availability guarantee. So likewise, we're going to build on what we've learned today and shared today to create a resilient community around these topics. We'll upload the final recordings to YouTube, and you can also find them at our websites. That's drand.love and randomness2020.com. You can continue interacting with other participants in the Telegram channel well after the conference ends. And you can tweet at us either through @Protocol Labs, that's 2 L's in the middle, Protocol Labs, or ETH Global. The event hashtag is hashtag random2020. We especially look forward to hearing about new sources of randomness and new uses for randomness. And so on behalf of Protocol Labs Research, ResNet Lab, the DRAND team, ETH Global, and the League of Entropy, I want to thank our speakers and all of you for joining us today. And with that, may all of your randomness be good randomness. See you next time.